Hi, thank you to the folks on Zoom for joining us. We will get started in a little bit. So once again, thank you, and thank you for your patience. No, it's okay. If you want, I can come up and do this after. But what you have to do is you basically use paper and then put that presentation. That's about it. Are you guys ready?
Sorry, is Letitia here? Oh, hi.
Okay, I believe we're ready to begin here. Hello, everyone. Welcome online and in person to Concordia University's fourth space. Thank you for joining us for CANSSI Quebec Postdoc Day, a day of exciting research in statistical sciences. Before getting started, we'd like to let everyone know that we are streaming to YouTube live from fourth space, which is located on unceded Indigenous lands here in Tiohtià:ke, Montreal. I understand that we have many guests today external to Concordia, so allow me to introduce you to fourth space. You are in Concordia's knowledge mobilization public space. We work with faculty, students, and staff to activate ongoing research projects and major initiatives with the goal of co-creating knowledge and building community. And we do so by producing daily hybrid activities that are free and open to the public. If you do have any questions for our presenters, you're welcome to raise a virtual hand or use the Zoom chat. For those of you here in person, please raise a hand and we'll be sure to get a microphone to you. So welcome in once again, and I'll pass the floor now to your MC, Melina Mayot.
Good morning and welcome everyone to this first CANSSI Quebec Postdoc Day. I want to thank you everyone. A special thank to Christopher Plensik, who was of a great help in the organization of the event, and thank you very much to all the speakers who agreed to present today. So I'll make it very short. I'm happy since CANSSI wanted to have this support and expand researchers, so postdoc researchers network. Feel free to have coffee, food, and to stand up and grab something during the talks or before and after the talks. Each speaker has 30 minutes to present, and it will be followed by 5 minutes of questions. We have a very tight schedule, so I'll ask the speaker to respect their time. And after the presentations at 4, there will be a reception upstairs on the 9th floor of the LB building, so you're all welcome to join us after. Donc, merci à tous d'être venus. Et si vous n'avez pas compris en anglais, la journée va être longue. Donc, je vais juste tout de suite passer le micro à notre première présentation ce matin. So, Lenin Del Rio Amador.
There's a clicker here if you want.
Perfect. Hello, my name is Lenin Del Rio Amador. I'm a postdoc fellow at UQAM under the supervision of Mathieu Boutreau. And today I'm going to be presenting a global view of ENSO floods correlations and the future socioeconomic impact of floods based on hybrid simulations. This work was started by a former postdoc, David Carroza, still under the supervision of Mathieu Boutreau. And so the model was initially developed by them, and what I'm showing here is the development of the model and further applications of it. Okay, so we all know the importance of trying to predict the impact of floods because of the large impact, socioeconomic impact of floods. And why this model? First, because we need a global view of past and future socioeconomic impacts of floods. Usually this is done using hydrological models, but those models are limited if we want global applications because of their high computational cost. So for a region, this is very useful, hydrological models, because it gives larger resolution. But if we are interested in global applications and for a very long time series, then hydrological models are limited. And also hydrological models easily integrate exposure and vulnerability with climate impact. Because of this, there are studies at the global scale on long-term projections and the influence of ENSO flood hazard and risk. If we, for example, we want to understand the impact or the influence of ENSO on the occurrence and the impact of floods globally, we are limited using observational data to only a few decades. So we need to expand on that. So for that, we need to build a modeling platform that includes climatic, environmental, and socioeconomic factors. In order to do that, as I said, David Carroza and Boutreau developed this global flood risk modeling framework using machine learning and climate models. So it more or less established a bridge between climate science and, in this case, catastrophe modeling and risk analysis. And what I'm going to do first is more or less trying to explain how the model works. First, we have a fitting step where you use historical climate outputs or climate observations, that is precipitation and temperature, and you use a random forest model to predict the occurrence, that is flood or not flood, for a given observational period from 1985 to 2007. And then if there is a flood, there is another component of the model that predicts the impact of the flood. This impact is measured in terms of population displaced by the flood. This is the measure that we choose to measure the impact of the flood. And this is all the fitting part of the process. Of course, we not only consider precipitation and temperature, we also integrate many watershed and socioeconomic characteristics. That is, we have 32 predictors that are from the watershed and socioeconomic characteristics. So that is porosity of the soil characteristics, and so on. And so for socioeconomic, we have population density and GDP per capita. This is all global distribution, so that covers the whole planets. So the same watershed and socioeconomic characteristics were used for simulation, but the difference is that we changed the climate data, precipitation and temperature, from observation to climate model outputs. For this, we choose the CESM large ensemble model that provides us atmospheric conditions up to 2060. And this allows us to not only have a much larger input for creating event sets, but also to project for the future up to 2060. So we try to measure the climate change impact on the occurrence and on the hazard and risk of floods. Instead of only having a few decades of observation, we're able to then create 3,200 years, that is 40 members for each climate model output for 80 years, that is 3,200 equivalent years to get statistics from. This is some of the scores that allows us to make the verification of the model, how well it works. And first, we need to measure the skill of the classification component, that is the occurrence component, if there is flood or there is not. And here we use 3 different models: a random forest, a logistic regression, and a generalized additive model. And the 3 of them have similar skill scores, with the highest score coming from the random forest. So for the observational period, that's the model we use, the random forest. That's the one that was published in the original paper. And then for the impact component, we also use a random forest for regression here. And I'll show you here the two skills. And I would say that there are good skill scores compared to what is usually available for these models. This is all done in the observational data. Then we by replacing the observational data with CESM outputs, we create these large event sets. So we were able to actually create 1 million equivalent years of floods all over the world. And this is the validation of these event sets compared to what was seen in the observational data. So of course, the perfect agreement would be the red line there. And we would say that we're not that bad. So the event set actually replicates what is usually observed for only the period of 1981 to 2020. This is where the period where the validation was done, but the projections are actually from 2021 to 2060. So we have 600 years, 1,600 years for each part, one for historical period and then for the future. So the first application of this model is on the influence of ENSO on flood risk and impact. So what I'm showing here is just the ENSO GMA index in the red and blue bars and gray bars there. Red are for the El Nino phase, blue are for the La Nina phase, and gray is for the neutral. And I also show one example of the probability of occurrence of floods that was computed for a given location. When I say location, I refer to one of the basins. We divide the Earth in 4,734 basins at level 5, level 5. And what I'm showing here is just the time series of probability of occurrence predicted by the model and how it correlates. So what we compute is how it correlates to the ENSO index. So we did that. So we computed this correlation for each climate model output, for each CSM model output. That is, we actually have, instead of having only a few decades from observational data, we actually have 1,600 years time series for each location that we can correlate to the ENSO cycle. That gives us much larger confidence levels in the correlation, of course, at the expense of replacing the true Earth by a simulated Earth from CESM. So this correlation was computed globally, and the results are shown in the first map on the left. So we got a 55% of the year with larger significance level than 95%. And this is very good. For example, the only group that gets similar results, there's a very powerful group located in Netherlands under the supervision of Professor Ward, that this is very powerful hydrological model group, hydrological group, and those are the only ones that provides us with this kind of stories at the global level. And they can only get 37% of the year with confidence level above the 90%, because of course they are limited to only a few ENSO cycles. They can only use observational data since 1964 to present, and because of that, of course, they don't have a very long time series to compute correlations. So in our case, since we have this very long time series of simulations, we've got much larger confidence level, again, at the expense of replacing the true Earth by a simulated Earth. But of course, we also know that CESM is very good at replicating the actual atmospheric conditions. Okay, so moving on, we can, with our model, we can get the average population displaced for all years and the average GDP disrupted for all years. If we know the population that is displaced, we just multiply that by the GDP per capita, and what you get is the population, the GDP that was disrupted because of the flood events. So this gives us not only a view of the population displaced, but also of the economic impact of floods. And with that, we can obtain how these measures of impact, population displaced and GDP disrupted, correlates or relates to the ENSO phases. So how many, so how large was the impact during the El Niño phase, and how large was the impact during the La Niña phase? And the results are shown here for both phases, and I would say that they kind of agree, more or less agree well with what is usually seen using hydrological models, with some discrepancies. First thing is, since El Niño and La Niña phase are opposites, we would expect to have opposite patterns of impacts during both phases. So wherever it is red in one map, it should be blue in the other. Our results are the maps in the left. In the right, you have the results that are obtained using hydrological models by Ward et al. And as you can see, since they don't have this large significance level, it's not easy to see these opposite patterns for a short period of time, as was reported by Ward et al. On the right. But we do see this kind of opposite patterns in the left that should reveal if you have long enough time series. Now, these measures of impact are normalized. So it's not just the population displaced, it is the relative population displaced that is relative to what is usually the impact considering all phases, not only the El Niño or La Niña phase, but consider all phases. So all measures are with respect to the baseline impact. And these patterns reflect very well the distribution of precipitation actually all over the world. So if you compare with the literature, you see that the impact measure that we use correlates very well with the patterns of precipitation. Now, the second application of our model would be to project the impact up to 2060. That's something that is not easily, you cannot usually do at a global level using hydrological models, again, because of the computational cost. And in our case, we did that. First, we need to replace the population with some projection up to 2060. For doing that, we use the data from SDAC, shown in the left, and we also need some kind of a scenario for the future. In this case, we use SSP5 for the future of the planet, a projection of the socioeconomic economic growth and I would say carbon emission for the future up to 2060. And we also need to replace GDP data with some projection up to 2060. So we're not only using CSM, so climate model projections, we are also using GDP and population projections up to 2060 in order to project the flood impact. Okay, first thing is we can no longer use random forest to predict, because we all know that random forests are not good at extrapolating. So they perform very well in the domain that it was trained. But if you want to project, you need to replace the random forest with some model that is able to extrapolate. But still, the random forest is very useful because it allows us to first identify what are the originally we have 41 predictors from the socioeconomic characteristic and basin characteristics and climate. So we have 41 predictors, but not all of them are too relevant. So random forest allows us to actually know what are the most relevant in order to build a simpler model that is able to extrapolate. And it also allows us to identify possible interactions and nonlinear transformation that should be done in the original data in order to have the best model possible. So using that, we kind of build two different statistical models, one based on just, again, linear regression with transformed co-predictors. And we also build a best GLM, so we choose the best predictors for each region in order to extrapolate. We also divide the Earth in many regions with similar climatic and socioeconomic characteristics, to have, instead of only one global model, we have actually 28 different regional models that we train and we use for extrapolation. And this is the validation of the three in the observational periods. So I still keep the random forest for reference, right? So these are the skill score for each of these regions that we divide the Earth. And this is the skill score for the occurrence component of the model and for the impact component of the model. And among the transformation that we made of the co-predictors, we split each co-predictors of precipitation and temperature into climate and anomaly components. And we also included an interaction term between the anomalies in temperature and the anomalies in precipitation. We made some other transformation on base GLM on population and GDP for it to be more Gaussian. And we also made some transformation in the response variable for impact. So with that, we were able to project the predicted probability of occurrence of floods up to 2060. And what I'm showing here is a comparison in the period 1981-2000 and the period 2041-2060. Those are the impacts, the occurrence probability at the top. And at the bottom, you see the difference between these two maps. That gives us how the probability will increase or decrease for each region globally. Red regions means that the probability of occurrence of floods will increase. Blue means that they will decrease with climate change. Or at least this is what we try to assess with this project, right? How the climate change will change the probability of occurrence of floods for the future, and also the impact. So So here you see that there are many red regions. That means that we have possibly we will have more floods in those regions, but this doesn't necessarily mean that we have a larger impact, because sometimes the regions correspond to regions where we have more GDP increasing. That means that we have more investment in contention measures, and maybe we have a decrease in the population in those regions. That means that we have lower impact because there will be less people affected by the floods. So this is what we get in terms of predicted impact for the future. So you see, for example, here in the left, you have in the east coast of the US, that an increase, you can expect an increase on the occurrence of floods for the future. But if you see the impact, you see actually a decrease in the impact. So that means that, for example, the population projected at 2060 may be decreasing in those regions, GDP increases, and this is negatively correlated to the impact of floods, because we are supposed to have more investment maybe in these regions. In any case, we can analyze these maps and try to give some meaning to the correlation that we see with each predictor using this model. And one experiment that we made was to freeze the population at the beginning of each period. So we freeze the population and the GDP at the beginning in 1981. So we say, okay, let's assume that the population won't evolve from 1981 to 2020, and only climate change, only climate varies in this period. And we have the experiment where everything changes in the same period. And this allows us to assess, okay, how much of the impact comes from the climate and how much actually comes from the socioeconomic characteristics, right? And we did that for the past. So we freeze the population in 1981, and we did that for the future. So if the population freezes, the population and the GDP freezes with the values of 2021, what is the expected impact of floods for the future up to 2060? And this is what I show here. So in the left is we have everything changing, population, GDP evolving up to 2060, and the right is we freeze socioeconomic characteristic for the future. So population and GDP are not changing after 2021. And then if you subtract the two maps, you see how much of the impact actually comes from the socioeconomic factors. So climate evolves the same way in both maps. So the difference in the bottom only comes from GDP and population changing in the future. So this is a very useful application of the model, and we of course we can try to make different experiments. We can actually freeze the climate change, only leave a population and GDP change in order to have different assessments of climate change for the future. And I think this is something that is very original of this kind of models, statistical models, because for example, hydrological models, you will see the impact of floods in terms of volume of water that is accumulated for precipitation and rivers and so on, but you cannot see directly how this impacts people and economy. Right, and with this statistical model, we're going to integrate both. We can see climate, and you can also see the socioeconomic variables, how they influence the impact of floods. Okay, so these are the conclusions. So first, I repeat, our results rely on the ability of the CMB framework to replicate the actual occurrence on the impact of floods, and also on the skill of the climate model to replicate the actual atmospheric conditions of ENSO events. Again, we're able to project, we're able to obtain very long time series and simulate very large event sets globally, because this is a very cheap model in terms of computation compared to usual hydrological models, but it relies on the ability of CSM to replicate the actual world. Using this approach, first we obtain similar distribution of normalized flood impact anomalies that compared to known global patterns of ENSO-induced precipitation. There are many studies done on ENSO influence all over the world. So this is a key comparison that we made. And it kind of agrees well with the expected impacts, with the expected patterns of precipitation for each El Niño phase. There is relative good agreement with previous studies on floods risk based on historical data about global and regional scales. There are only a few studies at global scale, but there are many at regional scales that we can compare with. You have some discrepancies, but you also have agreement with many of them in many regions in Australia, in the US, in Europe. So that gives us confidence in the quality of the model. And once we have this confidence, we can improve the signal to noise ratio by allowing us to observe more frequent opposite patterns in flood risk for the warm and the cold phases of ENSO based on this very long time series of simulated data. There is larger global coverage of a statistically significant correlation on impact anomalies between flood hazard and ENSO. And we also see some symmetry breakage in some regions. So there is no always opposite patterns for Niño and La Niña phase. Sometimes you can identify some symmetry breaking in these patterns. So both anomalies increasing. So anomalies increasing for both the Niño and La Niña phases. That is very useful. So, for example, in terms of in the insurance industry, you could try to so you can diversify spatially using the results from this model, but you can also try to diversify temporally if you know that, for example, the losses you will have during the El Niño phase will be recovered during the La Niña phase. But if both phases predict an increase in the impact of floods, then you have a problem there. So this kind of conclusions is what we try to then assess using the results of this study. And this model gives us the ability to predict socioeconomic impact of floods using future atmospheric and socioeconomic conditions at the global scale, and to assess the individual influence of climate, environmental, and socioeconomic factors on flood risk. Thank you. So I think I have 5 minutes still. Yes.
Did you look at the corresponding problem with droughts, the mirror image of flooding? Because I think that droughts are even more serious than flooding.
We have models for tropical cyclones. We have models for wildfires, but not drought yet. So we would like to have similar models for drought.
Because everybody is interested in that as well.
Yeah.
Because the thing is that flooded areas like the Florida Everglades is flooded, but there is lots of vegetation there. If you have a desert like the Sahara, then nothing grows there. That's a lot more serious.
Yes.
Flooding you can deal with, but if you have no water, you're really stuck, unless you have irrigation. But if there are no nearby rivers, then what can you do?
Yeah.
Unless you're in the middle of the Sahara Desert. Where do you get your irrigation water from?
Yeah, we're trying to build kind of this model for different, for a very wide CAD modeling framework. So until now we have wildfires limited, but we have some model for wildfires, tropical cyclones.
Because this is very important for Canada, as you know.
Yeah.
And not only because here talking about the world, but Canada is of importance to all of us here.
Yeah, exactly. So I'm starting a project next month that is only focused on Canada for
very good.
For floods, and maybe we'll.
And how about for us here in Quebec?
Not yet. We don't have any results. Not me, at least.
Okay.
So there is a PhD student that got some results. He's working now at cooperators, but he got some results for Quebec, for whole Canada.
Yeah.
Using the similar framework with improvements.
Yeah. Okay. Thank you very much.
Okay.
Yeah, sure.
You allude in your presentation that GLM were inherently better than random forests at extrapolating. Can you tell us a little more about this? Aren't all models bad at extrapolating?
No, it's random forest is not good at extrapolating because it can only work in the training domain. Okay, if the value is larger than this, predict this value is lower than predict this value. But what happens up in the domain, then the same table, right? I'm not say, okay, this will is further than what I already predicted for the past, right? That's why you cannot force. But if you build a linear model or generalized additive model, right, in general, you can for the future. Of course, you need to be careful because if you introduce large non-linearities, then you can blow up for the future with your predictions. So you need something that is still kind of near in order to extrapolate and to be confident what you are getting for the future. But comparison was only done with that. We can say, okay, we have a model that is as skillful as random forest, but we can also use that model for extrapolating.
Thank you.
Okay.
So talking about the random forest, did you also use some sort of deep learning algorithm for the same task?
Yeah, in the original paper, right? So the results on the paper are just for in the supplementary material, we show results for linear regression and logistic regression, and also for neural nets. So we trained 3 different neural nets, and the skill was very similar to that obtained with random forest. But the problem with neural nets is that you lose a lot of interpretability. So this kind of assessment that you can do, okay, we freeze the population, we freeze the GDP, what will happen in the future is hidden inside the black neural nets are. So you have a very skillful model, but it's not easy to interpret. That's why we kind of try to focus more on linear and generalized additive models instead of neural nets, for example.
All right. I have impression that usually random forest overfit the data, and sometimes I feel like the neural nets are, for example, I saw that you have a area under curves that's like the maximum is like around 0.9. So was it in the test data or the trained data?
It was always in the train period for out-of-box validation, of course. So we have a 70-30 partition for training and validation that many times in the past. So we try to always perform validation out of sample validation.
Okay, thank you.
Are there any other questions? We have time for questions. Okay.
Oh, sorry.
Yeah, time for one.
Sure, it will be a quick question. Hi, it was a really nice presentation.
Thank you.
I just wanted to ask regarding, in your presentation, you showed there was a socio-economic impact and one because just of the climate, right? I'm just curious about the impact in my area. So I'm from the northeastern part of India, which has floods all the time. And I'm pretty sure it's like the south of China as well as the northeastern part. But when I see in your plot that it was white for the socio-economic, meaning that it has very less impact, like even with the growing population and everything. Can you?
Yeah, these results, I think they come from the fact that the impact is negatively correlated with GDP growth. So if you have that's the same that happens in China, for example. The thing is, for example, in China, you have the population is expected to decrease actually up to 2060. So they actually achieved kind of a peak of population and then they start decreasing. I think in India, this is not the case. The population is expected to keep increasing up to 2060, but the GDP in India will also increase. So more GDP supposedly means more investment in contention measures, more people, for example, will increase in urban areas that already have a kind of all the infrastructure there. There's no growth in terms of infrastructure and impact directly of floods. So maybe even if the climate change implies an increase in the precipitation there, that not necessarily means an increase in the impact because of GDP and population also evolving into the future. So that's the kind of a study that you can not easily do using other approaches, because you cannot only look at precipitation, you also need to look at socioeconomic factors.
Thank you.
You're welcome.
Thank you, Lenin. So now let's welcome our next speaker, Arthur Chaton. English or French? English?
Yeah. We're going to switch out mics, actually, just so it's easier for you guys. Sorry. Oh, my bad. And we'll just get this right up there.
Thank you. Yeah, test. Okay, perfect. Hi all, I'm Arthur Chaton, a postdoctoral fellow at the University of Montreal. And I'm really delighted to be here today to present you our work on personalized dynamic pair learning for prediction. So first, it's a joint work with Mireille Schnitzer at UDEM, Robert Platt at McGill University, Michel Bailly and René Levesque at the Centre Hospitalier de l'Université de Montréal. I will also thank the data owner of the CHUM and Ivado to funding this work. Okay, First, by prediction, we mean the action to map certain feature of the world to another feature on the same world. For instance, we can map the daily electricity demand to the temperature or price and variance using Poisson's characteristics. So the goal of prediction is to obtain, the mean to mean prediction is to obtain a prediction model, which is simply a mathematical rule derived from empirical data, which map input X to an output Y. So our goal as prediction modeler is to find a certain function yielding accurate individual level prediction. But it's not so easy because we can use many algorithms which produce all different functions. For instance, we can use parametric regression, penalized regression, spline regression, tree, forest, neural network, and even more complicated methods. And it's even more complicated because each of our modeling choice produce also different function. We can produce different function by considering different variable selection procedure, considering different functional form in the model, interaction, tuning parameter, such as number of tree, number of forests, etc. But how do we choose the best function for our application? To answer this question, Van Dalen and his colleague propose a superlearner, which is an ensemble method based on the stacking algorithm from Brayman. The idea is to keep the best of all methods in one method, or to choose the best performing one. But keep it in the head, we want to keep the best of all methods in one. For this, they use a constraint linear regression, classically by setting all the way to be non-negative, and then sum should be 1. So at the end, we can obtain a weighted prediction of all methods. For this, they use almost aggressively cross-validation procedure to obtain a prediction for each learner, and learner is being the method in this context. And then they will use the linear regression to obtain a coefficient associated with each model. But I have a nice picture for this. So in gray, we have our dataset. The first step of bootstrapping, of cross-validation is to split the dataset in some fold. For instance, we have 3 folds, 1 red, 1 blue, and 1 yellow. Each of the fold will be a validation fold, and the other one will be training fold. So, okay, I don't have the cursor, sorry. For the first fold, we have 1 validation dataset, 1 training dataset. In the training dataset, in green, for instance, we will fit each of our learners. For instance, here we have, for instance, a GLIM, a nightly adaptive lasso, an SVM, and a GAM. We'll train all this learner on the training dataset, predict on the validation one. And we will have a vector of prediction on this validation set. We keep on the other fold. For instance, the blue will be the validation fold, the red and the yellow will be the training dataset. We'll fit 4 other functions, we'll predict on the blue dataset, and we'll obtain another vector of prediction, and so on each fold. Then we can obtain a so-called meta-level dataset, which we have all the observers, the actual outcome, and all the prediction for each method and each fold. And then we can use this meta-level dataset to fit a kind of meta-regression of meta-learner. Classically is a non-negative least square. And the idea is just to obtain kind of linear regression with a coefficient alpha associated to each method. And this is in our function, no superlearner function to predict. Now we come back to our analytic dataset. We will fit each of the method in our whole analytic dataset, and we can plug in all this function in our superlearner function. It's restarting. The computer restarts. Sorry. Nope, not my computer. Always on me. It's okay? Sorry. Yeah, exactly. No problem. Yeah, this one. Yeah, I will send you when to go to the next slide. Okay, perfect. Okay, well, next slide, please. Okay, but when in this work we want to go a little bit further by considering both dynamic prediction model and personalized prediction model. By dynamic prediction model, we mean that the prediction or the prediction model will be updated over time as new measurements become available. The goal is to obtain the most useful information at the current time for the user. And by personalized prediction, we mean that the prediction is mainly based on the individual characteristics. In this way, we can obtain more accurate predictions, specifically tailored for the individual, for instance. But be careful, because when we see personalized prediction, it's often not really individualized. It's more stratified prediction, because we have personalized at the certain subgroup or stratum level rather than the individual level. So an objective is to propose a personalized dynamic superlearner by extending the superlearner to be dynamically updated over time and by making personalized prediction at the individual levels. Next slide, please. Thank you. So for this, we are based on a recent paper from Ivana Malenica and her colleague, which proposed kind of similar approach, but for time series. And we adapt this algorithm for dynamic prediction, and we propose new ways to validate the resulting prediction model, which was missing in our paper. Next slide, please. Okay, I will make on one end the dynamic superlearning, on the other end the personalized superlearner, and we'll merge both after. So let's start with dynamic superlearner. The idea is similar to model refuting. So you just have a new prediction model at each time. So we will fit a new superlearner over time as new measurements become available. The idea is we can consider, even if we have the same candidate learners, the method in our superlearner, they don't have the same contribution over time. For instance, for the first session, maybe the GLIM will have more weight because is less flexible but more robust. And over time, we can have like random forest will become more interesting because it's just more flexible but need more data in gray. However, we need a specific cross-validation scheme due to the temporal calculation and to avoid data leakage. So we can use two different types of cross-validation. The rolling origin cross-validation, which just splits the data in different folds. So the first fold, for instance, we will train our model in the 5 first session, let's say, and we validate on the 6. For the second fold, we will train our model on the 6 first session, we will validate on the 7, and so on. So we will have always the same data. We will just increase by 1 for the validation fold. But we can also consider rolling windows cross-validation by considering the same windows of time, for instance, 5 observation, and we just shift over time from one session. For instance, for the first fold, we will train our model on the first to the 5 session, validate on the 6. For the second fold, we'll train for the second to the 6 session, validate on the 7, and so on. All have some advantage and pitfall, but happy to discuss it after if you want. Next slide, please. Okay, for the personalized superlearner, the idea is to leverage 2 data sources, the individual of interest, E, and the historical data, H. The method in the superlearner are fated either in E or H and or E. I have a little typo, I'm sorry for that. So we will fit our method either from the characteristic of the individual I or on the historical cohort H. The idea in our dynamic context is to use all the previous data from the individual for which we want to predict to personalize the prediction because we can more autocorrelation in this. And the final prediction is based on both sets of learners combined in our superlearner. Next slide, please. Okay, here we can go to the algorithm for the personalized dynamic superlearner. The first step is to fit a library of learner on H, on our historical cohort. By library of learner, it's just a stack of methods. We can also fit another library of learner, which can be the same or a slightly different one, on the training set from E. And third step, predict Y on the validation set for both historical and individual learner. So 2 or 3 correspond to the cross-validation step in my first figure. Then, after the third step, we will have our meta-level dataset. And on this meta-level dataset, we can make the same thing as the canonical superlearner by regressing Y on both the historical and individual prediction to obtain the weight of all of learner, which corresponds to the PDSL formula. And then we can predict Y for the next time using both historical and individual learner fitted on all available data and plugging the resulting function in our PDSL formula to obtain a final weighted prediction. Next slide, please. Thank you. Okay, and now how to validate this model? Because the gold standard in prediction modeling is to develop making an internal validation and then an external validation. External validation being the gold standard. By external validation, we just mean to validate the prediction of individuals not used for training the model and from a slightly different population to see the robustness of the score. But external validation is not possible by design for the PDSL because we're in a personalized prediction context and we want to predict for one individual according to his characteristic. So predicting on other individuals doesn't make sense. So we can make internal validation, but we need to account for the temporal nature of the data. And so we suggested a forward nested cross-validation approach by nesting 2 cross-validation schemes. The first one is the inner loop corresponding to the training of the PWSL. So it's the orange and green part. We'll train or we'll make a rolling cross-validation in the orange part to obtain meta-level dataset, and then we will compute our PDSL formula or weight on the green part. And we also augment it by another loop of cross-validation by considering one observation further in the time to validate the prediction of the POSL. And by making this loop for all available time for the individuals, we can obtain a vector of prediction similar to the classical context in prediction. And we can compute some performance measure over the outer lobes. Next slide. Okay. And now I will present you an application of this method in nephrology. Okay, patients with chronic kidney disease must be transplanted because we cannot deal with medication or drugs. But currently we are facing a transplant shortage. We don't have a sufficient number of kidney transplants, kidney graft. So patients should be dialyzed until the transplantation, if it ever happens. By dialysis, we link her to a kind of big machine which filter their blood. It's really hard for the patient, it's really hard to monitor for the clinician. So to giving an idea, it's almost 6 hours each 2 days from several years or until their death. So the clinician considers that better the blood volume filtered, the better the dialysis is. Not really the blood volume filtered, but it can be a good proxy, pedagogical proxy for this presentation. And achieving high volume time after time across patient population is really difficult for clinicians. And mainly because I must continually reassess multiple parameters, refresh in each session, and also consider specific characteristics for the individuals and time varying characteristics. So it's a very difficult task for which the PDSL have great potential because we are in a context highly dynamic and individualized. Next slide, please. So for sample, we include patients undergoing chronic hemodiafiltration filtration, which is a specific dialysis technique on which we focus. At the term from 2027 to 2021, we have included almost 500 individuals for almost 150,000 observations, with a little bit more than 300 sessions per individuals. The outcome volume ranged from 8 to 40 liters, with a mean of 27.4. And clinicians consider recent research in hemodiafiltration consider a good outcome volume at 24 or 23 liters. And it's interesting because this dataset have only a few missing data with only 2 predictors, and they have each less than 1% of missing data. Next slide, please. Okay. For the candidate linear, we consider 5 candidate: a linear regression, a lasso, a ridge, a multivariate adaptive spline mass, multivariate adaptive regression spline mass, and extreme gradient boosting. With all the predictors available, but also with only the 5 more important predictors according to random forest importance measure. So we have 10 learners, and we increment this set with another one, which is the arithmetic mean. The idea is it can help to reduce overfitting in the meta-regression. So at the end, we have 11 candidate learners for both individual and historical learner. We will use the same. For the cross-validation of the individual learner, we consider both rolling origin and rolling window. So at the end, we have 22 individual candidate learner. And we have 3 different PDSLs, convex, ensemble super learner. The idea is just we have the weighted regression with the sum of weight is equal to 1. We have also a non-convex ensemble super learner. It's the same thing, so the sum of weight are not fixed to 1. It can be slightly higher, slightly lower. And we have also a discrete learner, which is just, instead of fitting meta-regression, we just pick the best performing candidate learner by optimizing some loss function, which is pretty similar to picking the candidate learner with the higher weight. Sorry. Next slide, please. Okay, so we have a whole sample, which is split in two different samples. We have 173 individuals used to train our hyperparameter for each learner, again to avoid data leakage. And we have a working sample of 300 individuals. For these 300 individuals, we will predict the outcome. Each time we will pick one individual to be our I dataset, so the individuals, and the other one, the 299 individuals, will be the historical cohort, because it will be kind of implemented in this fashion in the clinical practice. We'll have the patient, which is coming for his dialysis, and we will use all the other session of the previous patient in the center as historical cohort, and we update it dynamically. And we will train and validate in a temporal way, as described previously. Next slide, please. Thank you. Okay, a lot of figure, I'm sorry for that, but we'll pass very quickly on this. On the top, the first three panels are just the composition of our meta learner for the two first one. It's just in the left, the number of non-zero weight. So it just indicate if the learner, candidate learner, will be present in will be used for the final prediction. In the middle panel, it with the cumulative weight. So it's slightly different. It's just the sum of all the weight over time. And the left is just the best one for the DSM. And it's interesting because if we see, for instance, the RWCV individual linear model, the third one in the A panel, it's presented almost one PDSL on 3. But if you see the cumulative weight is in the middle, we doesn't see it, almost disappear. It's because these contribute almost in a lot of sessions, but with a really small weight. In contrast, if you see the historical math, in gray it's historical and in orange it's individual, it's a reverse pattern. It's not really present often, but once it's present, you have a lot of weight in the prediction. In the bottom, we have the distribution of the learner over time. We can see that in the left panel, we have almost four learners which contribute to the PDSL over time, with more individuals than historical one, but just because we have more individual learner. And the really interesting figure will be the last panel, because we can see at the beginning, the cumulative weight for the learner, it's much more important for the historical learners than individual, because we cannot have sufficient information to, we cannot have sufficient information to train accurately the individual learner. But when we go further in time, we can see that we achieve a certain equilibrium, and then the individual learner obtain more importance. And then we can see that we have really a personalized prediction at the individual level. Next slide, please. Okay, R or performance metric, we consider a lot. Today I will present you quickly this one, which in the A panel, it's the median of the absolute error of prediction. In the B panel, the mean square error. And CD panel of just measure of calibration of the score. And again, in gray, we have historical learner. In orange, individual learner. And in pink, the POSL. For both MDAE and MEC, we can see that the POSL works slightly better than historical learner, and the individual learner also. And for the cPanel, for mean calibration, for the mean calibration intercept, but all learners correctly calibrate. But when you see the D panel with the calibration slope, which is the measure of the recalibration, you can see that historical learner work much better than individual learner and even than PDSL. This is interesting, and we can say that, okay, but historical learner is just better than PDSL. What is the interest? We have also, sometimes historical learner can be better, or PDSL cannot be the better at for each application, but it's the more robust over all the application because we have some sensitivity analysis and we can see a switch between the individual historical learner. So in some implementation, individual learner work better than the historical one. And even in this application, according to some metric, for example, if we see the discrimination was much better for PDSL and individual learner rather than for compared to the historical one. And we have also the same pattern for net benefits. Next slide, please. Thank you. And we have the evolution of the performance over time, but I only plot one individual learner, the linear model, and one historical learner, the XGBoost. We can see that for all metric, they have an increase of performance over time because we have just more observation. But interesting to see that for the linear model, almost at the 150 session, we can see that a huge increase of the performance. And it's interesting because you can see it's just the moment we reach the equilibrium between individual and historical learner. You can explain the equilibrium because just we have this learner are just more performant. And for the calibration, we see that the POS calibration on the bottom panel, it's very poor at the first time, mainly because we have some individual learner which just overfit, we just have some issue with the individual learner fitting. But the calibration hugely improve over time, which is a perfect calibration at the end. Next slide, please. Okay, so as I said previously, for this specific application, historical candidate learner outperform PDSL regarding the recalibration. And this can be explained because we have just too few training sessions for the individual learner initially, and the individual learner are taken into account in the super learner. But if just we want to begin to predict later, may improve the calibration, as you see. And we have some choice to, for instance, to have a very short training session at the beginning. If we increase it, we can also improve the performance of the PDSL. And again, as previously said, it's at least application specific. Result can differ in other contexts. So the idea is, okay, even if PDSL is not the most performing one in each session, it's the most flexible one. Because, or more robust one, because even if it's not the best one each time, it will be never the worst. And maybe just the more interesting things. We can also consider to using an historical super learner as a candidate learner for improving the first session or nesting the cross-validation because I considering like kind of discrete super learner, which all the candidate learner and the PDSL, we can improve the performance, but we need again to nest another cross-validation procedure. So it can be a little bit more complicated. Next slide, please. And we have again a lot of open questions on this very, very interesting topic. How can we deal with lagged value of predictor? Should we take only the last session, an average of the last month of the 10 last session? We have also a trade-off between the availability of predictor and accuracy of prediction. Much predictor we put, more accurate will be the prediction, but less usable will be the score in practice. What is the minimal sample size? What is how do we compute a number of cross-validation fault? how do we deal with missing data? How we can tune the hyperparameter of the learner. And a lot of applications we discuss in your paper, so if you're interested, stay tuned for seeing the paper. And I will be happy to discuss it after. Last slide, please. Thank you very much. So I will finish this presentation with three take-home messages. First, personalized dynamic superlearner can dynamically predict a repeated outcome, continuous in this application, but also binary outcome, while optimizing the prediction for the subject. We provide a way to evaluate such models where external validation is not feasible. And I will end with surely the more important message, because as modeler, we are always very interested in statistical performance or technical challenge for implementing the algorithm, but we need to look beyond by considering also the ethical issue of using machine learning, such as fairness of the method, and so on. So thanks for your attention. That's okay.
Thanks. In your combination methods, have you considered stuff like Bayesian model averaging? Which is, it's not quite the same combination algorithms you're using, but...
Yeah, for instance, we can use Bayesian adaptive regression tree. Yeah, totally. I'm not really familiar with Bayesian model, so okay. I don't use it to just avoid to some issue with this, but we can definitely use it.
Okay.
Anyone else online or in the space?
Hi, I have a question. If I understand correctly, you maintain one single model for historical data, right? For all the individuals, you have one model for.
Sorry, can you repeat?
So you have for each individuals, you have a single model for each individual, each person, and then you have one global model for like all individuals, right?
Right. If you want to, if I take a clinical case, a physician see one patient in front of him, he wants to predict his outcome.
Yeah.
And so we will have some models according to his characteristic, only his characteristic, and other models according to a pool of historical patients.
So I have a question. So if the data from each person is different, and this, do you see that the scaling of the data from each person is different, and how you deal with the difference in the scaling of the data?
Yeah, it's a good question. Thank you for this. Fundamentally, because all the data come from the same database, we have no issue with the scaling of the data. But in practice, to predict, we should all the same data or all data available. Maybe we can combine some model using on different, but the issue is because we want to predict for the individuals, it should be the variable for these individuals should match the variable on the historical cohort. Maybe rescaling the covariates could be interesting. That's a lot of literature on like kind of measurement error if the predictor are not measuring in the same way on the individual for which we want to predict and the individual use it for training. We have a lot of issue with miscalibration. So it's an important topic of research. And effectively, it's an important concept. Thank you for this. Thank you very much.
You're good. You're ready.
Yeah, good. Okay.
So this is working.
Okay.
Unfortunately, we can't use this. but it's here, so you could just switch with these, I believe. Yes.
Okay.
Is that okay?
Yeah.
All right. Everything is so great.
Yeah. Let me try.
Yeah, the laser's not going to work, so just.
Okay. No. So, can I stand here? Yeah. Okay. Hello, everyone. My name is Hong. I'm very happy today to present my recent work in the context of the COVID vaccine effectiveness estimation on the so-called test-negative design. So this is a joint work with my postdoctoral supervisors, Michael Schnitzer from University of Montreal and Denis Thibault from University of Laval. So the context is in the infectious disease, epidemics or pandemics or seasonal influenza. The public health data on infections are collected from the individuals obtaining the test. So it could be the test during the pandemic, and we have a lot of information. And for example, the PCR test for the SARS-CoV-2 infections. But in the non-pandemic context, we also have this kind of data. For example, the people to go to see the primary care physicians and then get the test, get the result. So for the latter, this test is almost completely driven by the care seeking when they're ill. But the former one, each individual gets the test and they will receive the outcome, either positive or negative for the SARS-CoV-2. So this test is going to be diverse reasons, depend on the public health reasons for getting the test. So for the clinical trials was designed to establish the vaccine of the effectiveness. Once the vaccine is rolled out, the jurisdictions might diverge from the test protocol. For example, the Canada, here there is a huge gap between the first doses and second doses. And the vaccine is used on the broader populations than the clinical trials. So there is a demand for the observational analysis to establish the effectiveness in the real world, the heterogeneity populations and the usage for the long-term periods. But the clinical trials cannot evaluate it. So the test-negative design is an observational study design that compares the outcomes in the people who had the symptoms characteristic of an infectious disease of interest and then obtain the test. So those who test positive are called the cases. Those who test negative are the controls. So test-negative design was originally proposed to study the vaccine effectiveness against laboratory confirmed medical attended influenza in Canada, and now it gradually formalized by a lot of researchers and can be used now to estimate the COVID vaccine effectiveness. So here is the causal diagram or the causal deck. I will use it to illustrate the data structure and the test-negative design. So suppose each of us has some vaccine status denoted as a V here. For simplicity, you can consider we are vaccinated or unvaccinated. Then we have some infections, I here, which is latent. So we probably have non-infections and we have no symptoms. Or we have some SARS-CoV-2 infections. That's the target infection we are interested in. Or we maybe have some other infections. So if we have the SARS-CoV-2 infections and other infections, we probably have some symptoms as COVID-19 symptoms. Then we go to the test. This is the version for the hospitalization. You get the test, you know the result. So for the covariance C here, which are the confounders, will affect both the vaccination, exposure vaccination, and the components of the outcomes. We have the three components of outcomes: infections, symptoms, and hospitalization. And we assume that all the confounders are measured. And for the unmeasured variables, the U, like our genetic information, we don't know about it, but they could affect all the components of outcome. but does not affect the vaccine, our exposure. So that's the causal diagram. You can see that there is a box around the symptoms and the hospitalization. It means we select data adjust or conditional on the symptoms and hospitalization. That's because of test negative design does. So test negative design selects the people who have the symptoms and who are hospitalized. So each individual in the test negative design has some symptoms and is hospitalized, but some of them has the COVID. Okay, that's the notations for our data. So for the complete data, the Z superscript C here, we have some covariance, vaccine status, infections, symptoms, and hospitalization. This is under the distribution P with the simple random samplings. So we define S the presence of inclusion criteria for the test negative design. That's the indicator of the I not equal 0. I equal 0 is the non-infections. I equal 1 is the other infections. And I equal 2 is SARS-CoV-2 infection. That's the target infections we care about. And then we have symptom equal 1 and hospitalization or test equal 1. However, our observed data only is the CV, I, and I S equal 1. Only S equal 1 can be included into the test negative design samples. So this data is under the distribution of the P of Z conditional or given the S equal 1 or TND distribution of the P. Note that it's the outcome dependent sample. It's maybe bias for this distribution. So, and a relevant outcome is the Y, is the 3 components of the I equal 2, the target infections, and the symptoms, and the hospitalization. So keep in mind that this outcome is not usual in the literature, and we call it the hospitalized symptomatic SARS-CoV-2 infections. So the typical analytical method is the logistic regression, and we regress the outcomes on the vaccine status and the measured covariance. So for the cases are those who tested positive, and for the controls are those who tested negative. And for the beta is the coefficient of the vaccine status. So under the 2 assumptions, the first one is the modeling assumption of the logistic regression. The second one is we call it the control exchangeability. It means that the vaccine has no impact on other infections. The vaccine is conditional independent of the having other infections leading to the inclusion criteria. Then the odds ratio from the logistic regression identifies the risk ratio of the association between the vaccination and the probability of the hospitalized symptomatic infections. Then the vaccine effectiveness is defined as 1 minus this odds ratio, exponential beta here. So the logistic regression target risk ratio, which is collapsible, and we can directly target the marginal risk ratio under the unbiased distribution P here. That's the probability of having the outcome of interest conditional on the covariance and vaccine status V versus another vaccine status V0, and it marginalized over the covariance. And Schnitzer, she proved the identifiability of this marginal risk ratio. If you're familiar with the causal inference, this marginal risk ratio is the causal risk ratio under the normal standard causal inference identifiability assumptions. Then she proposed the IPW estimator to estimate this marginal risk ratio. So for the IPW estimator, first we define the selection probability Q0 is a marginal probability of having the inclusion criteria for the study. And the main information is in this equation here. The right-hand side is the marginal expectation of the outcome. Left-hand side is expectation on the TND distributions. And the key point is the probability of the V and given C. That's the so-called propensity score functions. It's a model that predicts or outputs how many probabilities you receive this treatment or you receive this vaccination. So you give your information, I can predict how likelihood you receive the vaccine. So this probability, the propensity score, is estimated on the simple random samplings. So the question is here is how can we use the outcome-dependent samples to estimate this propensity score? So that's the last piece for the identifiability for the inverse probability estimators. Again, we rely upon the control exchangeability assumption. That is a conditional independent assumption. Conditional on your covariance, okay, conditional on your covariance, the vaccine does not have any impact on the controls on other infections. That's the vaccine is independent on the controls. I equal 1 is another infections is denoted as the control here. Then, based on this assumption, we have the identity in this part. That is, the propensity score can be estimated only by the controls using the TND data. Okay, that's the preliminary work for the IPW estimator. Built on this, we give the alternative identifiability formula using the debice inverse. First, we define the debice inverse as the omega V of the C here. That's the ratio of the selection probabilities. So in the numerator, you can see that's the selection probability S equal 1 conditional on the vaccine and the covariance. For denominator, the selection probability only conditional on the covariance C here. Then given the conditional TND expectation of the outcome, mu V of the C here, it means you give your vaccine status and give me your covariance, I can give you the probability, how likelihood you be get infected by the SARS-CoV-2. And the outcome Y equal 1 here. Then the outcome expectation of the marginal expectation of the outcome can be written as the equation 1 here. So for the equation 1, the left-hand side is marginal expectation of the outcome of the vaccine status V. Right-hand side can be identified as the expectation under the TND distribution in terms of the outcome model mu V and the debice inverse omega V here. And we prove that under the control exchangeability, the debice inverse are identified in the following two ways. The first way is the ratio of the propensity score. So for the numerator, that's the propensity score estimated by all the TND data, S equal 1 there. And for the denominator, that's the propensity score estimated only by the controls. That is denoted by Y0 and S equal 1 here. For the second way, the outcome probabilities. So for the numerator, that's outcome probability conditional on the covariance. For the denominator, also conditional on the V and C. So we can estimate these four models, and we can debice inverse. Okay, then we propose the estimator for the marginal risk ratio. Recall that that's our target parameter based on the outcome modeling. If we use the second way to identify the debice inverse in this form, then our outcome regression-based estimator only depend on the outcome models. So that's the two single robust estimators. And the following part is our main contributions in this work. And we want to use the semi-parametric or non-parametric theory to construct an efficient estimator for the vaccine effectiveness. And we still can use the machine learning method, and we can maintain the valid statistical inference to estimate the vaccine effectiveness. So we first derive the efficient inference function for the marginal risk ratio, and we propose the one-step doubly robust and the locally efficient estimator. And we can use any machine learning method for the estimating the nuisance functions and even converges at the quarter rate or the slower conversion rate to the truth. And then to estimate the vaccine effectiveness on the TND data, and we propose a three-step algorithm called the TND doubly robust, the tender, and we use the data splitting and machine learning method to estimate it. Okay, now I'll go to the more details about this tender. So first we derived the efficient influence functions for the psi v, let's say the marginal expectation of the outcome under the vaccine status v here. The efficient influence function is in this expression, and the whole deriving process is dependent on the unbiased distribution p here. And if you consider the influence function-based estimate, and these indicators, you can see indicator of y equal 1 and indicator of y equal 0 and s equal 1 will constrain the unbiased samples to the TND samples. So there are two main components for this efficient influence functions. So for the first component, the indicator is y equal 1 is only related to the cases. And for the denominator, that's the propensity score estimated only by the controls. And second component, the indicator y equals 0 and s equal 1 is only related to the controls. And we also have the debasing West omega v, outcome model mu v, and for the denominator, we have the propensity score and the M model here. That's also the TND probability of the Y outcome equals 0 given the covariance C here. And we give the estimator, that is psi v hat, which is the Pn of the phi v. Pn is an empirical mean, and the phi v is in expression. You can tell that it is directly derived from the efficient influence function. And this is also called the one-step estimator. And we explore the distributional Taylor expansion, also known as the von Mises expansion. And we have the main result summarized in this theorem. So that's under the identification assumptions and some conditions. Then the estimator satisfies equation 2 here. So equation 2 tells us your estimator, psi v hat, the distance between the psi v hat and the true psi v can be decomposed by 3 terms. So first, for the last term, that's the small op 1 over root n, which is asymptotically negligible. It's mainly derived from empirical process term. So to guarantee this empirical process term to be negligible, the 2 conditions are necessary. The first condition is to constrain the complicity of this phi v function. The second condition is to use the data splitting. And under these conditions, this empirical process is small op 1 over root n. And for the first term is R2 term. It's called the second order remainder term. That's the product of the nuisance errors. So we show that this second order term is bounded by this sum of the 4 product of the nuisance errors in terms of the propensity score model, outcome model, and debasing West, and the M outcome model here. Lastly, for the midterm, that's the Pn minus P of the efficient influence function psi v here. That's the sample average of the fixed function. Then we can apply the central limit theorem to get the limited distribution of the psi v here. So if the second order term is negligible, that is order of the small op 1 over root n, then equation 3 satisfies. It means that psi v hat is root n consistent and asymptotic normal. So the following question is, under what conditions does the second order remainder term become negligible? So we give the 2 corollaries. The first corollary is about the root inconsistency and asymptotic normal. We particularly give the 3 conditions. You can see that this is the condition about the convergence rate of the nuisance functions. For example, the first one, propensity score model converges in the quarter rate, in the slower rate. So if we have these assumptions, second order remainder term R2 is also negligible. For example, the quarter rate for the propensity and the quarter rate for the outcome model, and 2 product of the quarter rate is the root n rate, which is asymptotic. So under the assumptions 1, 2, 3, the R2 term is also negligible, and we apply central limit theorem and the Slutsky theorem. The psi v hat is root n consistent and asymptotic normal. And the limiting distribution is the normal distribution with the mean 0, and variance is variance of the efficient inflow function. So the take-home note here is we can use any machine learning method to estimate the nuisance function, even at a slow rate, but we can obtain the root n rate for our target estimator. Secondly, we have the double robustness. So recall that we have two models. The propensity score model is given your covariance, we can predict what code you receive. And the second model is outcome model, given your covariance, what is the likelihood you get the SARS-CoV-2. And depending on this model, the doubly robust, the main idea that is one of this model correctly specified, and our target estimator, our estimator for the target parameter is also correctly specified. That's the main idea of the double robustness. It means that the propensity score model is correctly specified, consistently estimated, or the outcome model are correctly specified. It's also consistently estimated. Then the second remainder term is converged to 0 in the probability. Then the estimator is also consistent. So the correctly specified the propensity score model and the outcome model will eliminate the second order remainder terms. Okay, so that's the two main results we have. We combine these two corollaries, we give the three-step algorithm. As I said, it's called the tender, the TND W robust, the W robust estimator. They simply have the three steps. The first step, we use the data splitting. We split the data into the capital J joint evenly sized folds. The second step is use the cross-fitting. We can use any machine learning method to estimate the nuisance functions, the propensity score model, and the outcome model. The third one, we construct the vaccine effectiveness estimator based on this efficient estimator psi we had here. That's in the form of the data splitting expression. Okay, so following part, I'm going to show you the simulations studies. So in the simulation study, we particularly have the three goals. So in the first goal, we want to conduct the sample splitting and use the machine learning method to assess the efficiency of our proposed tender. The second one is we want to investigate the double robustness of our tender. The third one is to verify the average of the 95 confidence intervals based on this efficient influence function that's the estimator under the machine learning or correctly specified parametric models. And we generate the data following this causal diagram, and we select the individuals who have the symptoms and who are hospitalized, as the test negative design does. And know that there is no effect of the vaccine on non-SARS-CoV-2 infections. That's the control exchangeability assumption that we relies on. So in the first study, we use highly adapted lasso. It usually kind of converge to the quarter rate for the nuisance function estimation. And here is the result from 2,000 sample size. For the beta EM, that coefficient, that's the coefficient of the so-called modification or the interaction term between your covariance and the vaccination. It represents the heterogeneity treatment effect of the vaccination. So compared with IPW estimator and the outcome regression-based estimator, and our proposed tender provides the comparatively smaller mean bias and the Monte Carlo standard errors. And our method can achieve average 95% coverage rate. Now here is the root n consistent for our proposed estimator. So x-axis is increased by the sample size. For the y-axis, that's the bias, the distance between your estimate and the truth, the risk ratios. And red dot plot is our proposed efficient influence function-based estimator. And the triangle plot is the IPW estimator. You can tell that the red dot plot converge to the 0 faster than the triangle plot. So for the second study, we want to demonstrate the double robustness. It means either propensity score model all the outcome model is correctly specified, it's consistent estimated, then our estimator is also consistent. Particularly consider scenarios A, B, C, D. A is both propensity score model and the outcome model are correctly specified. The C is one of them correctly specified, and D, neither of them correctly specified. So in the first three scenarios, you can see that the bias is relatively small, and compared with the last scenario, none of them correctly specified, and also the mean Monte Carlo standard error. So in the first case, both propensity score model and the outcome model are correctly specified. Then our EIF, efficient influence function based estimator, can achieve the 95% coverage rate for the truth. So finally, I will show you some real data analysis from INSPQ, administrative data set of the healthcare workers in Quebec, Canada. And this study is the time frames characterized by the Omicron BA.5 dominance period from July 3rd to the November 5th, 2022. Again, for outcome, those who tested positive are the symptomatic COVID-19 and hospitalized within the 14 days of testing positive, and for the controls are individuals who tested negative. And for the vaccination, V=0 for those who had the booster vaccine within the 6 months, and V=1, and V=0 is for those who received the final doses, that is 6+ months before the test. So we compare this to kind of the vaccine status. And we selection the covariance, the gender, female, male, and multimorbidity, yes or no, and epidemiological observation time frames. That's the results from the FOR method. So in the column here, we compared RPW estimator and outcome regression-based estimator and our proposed standard. And the last one is the standard, the traditional logistic regression method. And we use the generalized linear model and also use the machine learning-based method. We use the MARS. And you can tell that using the generalized linear model, RPW, outcome model, and the logistic regression give the same point estimator. But our tenter provides the relatively smaller marginal risk point estimator. And also using the MARS, the machine learning-based method, and you can see that the IPW and outcome model, this point estimator is slightly higher, but our tender provides the slightly lower than the generalized linear models. So the conclusion is for this real data analysis, against hospitalized symptomatic SARS-CoV-2 infections, to compare the booster vaccine within the 6 months versus the final doses administered 6+ months before the testing, and our proposed tender method, the vaccine effectiveness estimate using the generalized linear model is 35.0%, and using the MARS is 35.4%. Okay, so that's final discussion about our method. Our method is very sensitive to the extreme values of these two probabilities. Recall that this two probability is in the denominator of the nuisance functions. So if this two probability has a very smaller value, it will make this efficient influence function very large. So we can use the target-based learning, like the TMLE, to improve the finite samples. And also to deal with the unmeasured confounding bias or the class stratification bias, she, meow, and chicken, they took the double negative control approach to these two bias. Okay, that's my presentation, and we thank the support from CIHR, and thank you.
Anyone online or in this space have any questions? Anyone at all? Perfect.
Thank you for your presentation. Naive question, why do you use different machine learning method in your simulation and in your application?
All right, yeah. In the simulation, we use the HL, highly adaptive lasso, and in the real application, we use the math. The thing is, first in the real application, we have the co-author at Quebec. She implements the R codes, and we first try to install the HL, the package. It does not work in that system. So that's why we change to the math and use the math
Okay, thank
in
you.
the real data analysis. Yeah.
Any other questions? Okay, I believe we will move on to setting up for the next speaker.
Thank you very much. And the next and last speaker before the lunch break, Barkov Deka.
Doop, doop. On top, go ahead. You're unmuted.
Hello.
Perfect.
All right. I need to connect on. Hello, everyone. Hi, thank you for the invitation. My name is Bhargav Deka, and I'm a postdoctoral researcher, and I work with Professor James Goulet, who is here, and some of my team members, and my research lab is called Bayes Work, and the topic of my presentation today would be the online aleatory uncertainty quantification in probabilistic models. We use models to represent reality, be it the housing price data set, or maybe we are interested in stock prices. So if we want to look into patterns, we need models to identify patterns in them. Let's set the problem in a more simple way. Let's consider that we have some data which is represented in the red points, and we want to build a model to represent this data. For example, the black line here represents the model represents this data. Now, if we want a deterministic model, then we'll only have the predictions for this model. But if we want it to be probabilistic, meaning that we also want the uncertainty associated with each of the predictions, then we need to have some of these parameters that we use to parameterize this function to be probabilistic distributions, to have probabilistic distributions. But is it straightforward to do so? If we use the Bayes rule, because we can use the Bayes theorem in order to obtain our posterior for the parameters theta given the data, we'll use this formula. So in the numerator, we have the joint distribution, and in the denominator, we have the evidence. We see that it is difficult to obtain the evidence in most cases because it involves integrals that are either intractable, or in sometimes it can be tractable, but it will be in so large multidimensional domain that it becomes computationally really slow. But if we are able to do it analytically, meaning using closed form expressions, the integrals we can solve using closed form expressions, and we can do it online, meaning in real time when we'll collect data, we can process it, then we'll be able to scale to larger problems. So we'll be able to build probabilistic models for larger problems. Here I present the Jacques-Cartier bridge because I work in structural health monitoring. It can be any other large problem that you guys are interested in. Now, before going into uncertainty quantification, I want to talk about the types of uncertainty that are present in probabilistic model. For example, if I have a function like this, for example, the true function is given by g of x, which is the red line over here. We have the data points in magenta, and the black line shows our model. Now, there are two types of uncertainty that exist in the data. So one is called epistemic uncertainty, which is represented in the blue region here, and one is called the aleatory uncertainty, which is represented in the violet region here. So basically, the two total gives the total predictive uncertainty. Now, the epistemic type of uncertainty is reducible given that we have more data points for an identifiable problem, meaning that if we know that the true values for the parameters or the model parameters exist, if we collect more data points, we can shrink this type of uncertainty. Whereas the aleatory uncertainty that arises because of the inherent variability in the data, that cannot be reduced, because when we try to model complex practical phenomenon, it is impossible to know all the explanatory variables that can explain that particular phenomenon. We'll always lack some of the explanatory variables. Hence, we'll always have this uncertainty that cannot be reduced even if we collect infinite amount of data. The same example we can have now. Let's consider we collect more data points and we refine our model. So I can show that the epistemic uncertainty can be shrink to 0. So only thing that will remain is that violet region, which was the aleatory uncertainty. So we are not able to reduce this uncertainty and it remains constant. So we need to quantify this aleatory uncertainty. Typically, computing or quantifying the aleatory uncertainty is computationally demanding because we have to rely on grid search procedure or gradient based, so it makes it computationally demanding. Hence, we need a scalable approach in order to quantify aleatory uncertainty in our probabilistic model, meaning that we need to find a method that can do it analytically, and if we can do it online, then we'll be able to scale to our large scale problems that I spoke in my first slide. Now, because I primarily work with time series data in my research, so I rely on one specific type of probabilistic model, which is called the state space models. Now, state space models are used to analyze time series. For example, if I have a time series like that shown in red, what I can do is I can identify all the underlying patterns for this time series. For example, I can identify what is the baseline of this time series. I can identify what is the periodic pattern, as well as I can decouple the residuals from this time series. You can see that these are all the patterns, whereas the residuals we cannot identify because these are random. We do not know the source of it. So only thing we can do is identify kind of an uncertainty band that is associated with these residuals, which would be our aleatory uncertainty that we are trying to quantify. So in state space models, what we do is use an autoregressive process to represent these errors. So it is given by this equation where we have a hidden state, xar at time t. So it is connected from time t minus 1 to time t. So it goes from xar equal to 5 times xar t minus 1. This is the deterministic part. WT, which is the stochastic part. So this is assumed to be a Gaussian distribution with mean 0 and variance sigma square W. So basically it is the sigma square W, which is known as the process error variance parameter, is quantifying the aleatory uncertainty that is present in this time series data. Now, how we can quantify this uncertainty? Let's use a simple example in order to see how we can do that. For example, if I take this sine-like time series, it's a very simple time series. So we have in black, which is the function, and the red points here represent the data. And the violet region you see, it's the uncertainty that is present in the data. Now, if we use a variance parameter that quantifies this uncertainty and we consider it to be a very large value, so we are underfitting our model, or if we take a very small value, then we are overfitting our model. We do not want that. We want to identify what is the correct aleatory uncertainty that is present within this data. Let's just remove the function over here and look at just the uncertainty. These are all the error terms here, which can be assumed to be coming from a Gaussian distribution with mean 0 and variance sigma square. Now, if I have all the error terms available to me, I can use the empirical variance formula in order to compute my empirical variance. In this case, since the mean is 0, let's cancel this out. So we'll end up with this formula over here, which is basically taking average of all the W square terms. So I square all the W terms here and I take average, I'll get my empirical variance. And if we have large amount of samples, this empirical variance will tend towards what is the theoretical value, which is the expected value of W square for the parent distribution. But this process is neither Bayesian nor online. As you have seen that we need all the residual terms to be available for us in order to compute our empirical variance. If we want to do it online, meaning that we do not have access to all the data points, we're just observing one data point at a time. For example, for this entire time series, now we are just observing the first data point, okay? So in a Bayesian framework, the best thing we can do is start off with some prior knowledge. So we'll start off with a broad prior knowledge for the expected value of W square, which is representing sigma square. Let's keep this distribution over here and we'll come back to that. So using the prior for the expected value of W square and observing the data point, I can obtain a distribution for W. Once I've obtained the distribution for W, if we look at the formula, now we need to find expected value of W square. Now W is a Gaussian distribution. How do we obtain? We need a method that can quantify the moments for W square. In a group, we have developed this method called the Gaussian multiplicative approximation. The essence for the method is that whenever we have the product for two Gaussian random variables, we approximate it to be another Gaussian random variable, but all the moments associated with the Gaussian random variable, we can obtain it using closed form algebraic expressions. As you can see here, I have grayed out the equations because I don't want to focus on that, but we can do it. We can do it using closed form expressions. So you can obtain the expected value, the variances, as well as the covariances associated with this product of Gaussian random variables. Now, using GMA, we move from W to W square. So once I have a distribution for W, I obtain the distribution for W square. It's straightforward. I use GMA, I obtain all the moments. Now, how do we connect W square to expected value of W square? Because that's our main goal. We have found out another way that we can connect W square to expected value of W square. So basically, whenever I have a posterior for W square, I can obtain the posterior for the expected value of W square. Now, if you look at the figure here, where I represent the prior in blue and posterior in violet, there's not much difference between both the distribution. It's because we have just witnessed one data point and there is hardly any information to learn from it. But if we look at more data points, you'll see that the distribution or the posterior distribution, the variance for it is shrinking and it is moving towards what is the true value, which is represented in the red dotted lines. And if we move to the end of the time series, it has converged to what is the true value for the expected value of W square, as well as the distribution looks like a direct meaning that it is confident of the value it has converged in. Also from the data, you see that in the beginning, we had the large uncertainty. It's because we started with a broad prior knowledge And over time, as we see data points, we are able to quantify what is the correct elytary uncertainty present in this data. Now, this framework, where basically on a high level, we connect two steps. One is W to W square using GMA, and another is W square to the expected value of W square. We refer this process, this method, as the approximate Gaussian variance inference, or AGVI. AGVI is a Bayesian method, and you have seen that we can do the online inference. We can quantify our uncertainty as we see each new data point. And the best part is that we can do all the computations that you see in order to obtain our uncertainty. We can do it analytically, meaning using closed form expressions. Let's go a little bit more in depth of AGVI. Here, I'm going to represent what is the graphical model that I use in order to quantify uncertainty in state space model. For example, so in the beginning, I start with the expected value of W square, what we are trying to infer. We consider it as a Gaussian random variable represented by W square bar. It might be a little complicated to look at the notation right now, but W square, so it is W square, expected value, we normally represent a mean by a bar, so I consider it the bar, that's the notation for it. So as I said, we have a prior knowledge for the W2 bar, and then I connect to the square of the process errors, and then the W square is connected by a one-to-one relation with W, which is the process error. And this is because the moments are associated between W and W square. So the variance of W is basically the expected value of W square. So the moments, there is a one-to-one relationship between them. Hence, I represent it through an indirected line between both of them. And then I have X, the hidden states that I get from state space model. And finally, we have the observation Y that we connect through an observation model. And we want to do it recursively. We want to recursively update our hidden states as well as our posterior for the W2 bar. Now, for the prediction step, how do we do it? So we start from the prior knowledge for W2 bar, and we want to go and obtain what is my distribution or predictive distribution for W. For this, we rely on this procedure called the Gaussian conjugate prior, where when the mean of the Gaussian distribution is random itself. For an example, let's consider the Y is a Gaussian random variable having this distribution, having mean M and variance sigma square. Now the mean M is not a constant deterministic value. It itself is a random variable having its own hyperparameters mu M and sigma square M. So basically we need to marginalize out the uncertainty associated with the mean in order to obtain my predictive distribution for Y. So here I represent the equation in the Gaussian notation, and I'm not shown the full calculations here, but it's straightforward. So you can take expected value and variance of this equation, plug it in, and then you'll obtain what is the marginal distribution for Y. And you'll end up with this formula over here, where the mean is mu M. So it's this value, and then the variance is the sum of both the variances, sigma square plus sigma square M. Now, we want to use it in our context. So here we're going to replace Y with W square and M with W2 bar, as the expected value of W square is W2 bar. So this is how we represent the entire process. So we'll use the same equations as before. We're going to replace them with our notations here. So only thing is that the variance is 2 times of W2 bar. This we evaluated by computing the variance of W square using GMA, because we can obtain the variance for the square. So now, once we do it, we use the same setup and we compute our marginal for f of W square, which is given by this formula. So we'll obtain all this mean as well as this variance term. Now, once I obtain the distribution for f of W square, it's straightforward to obtain f of W because the mean is 0 and we know how the variance is associated. So the variance of W would be the expected value of W square, which is mu W2 hat. So now, from mu W2 hat and sigma square W2 hat, we obtain what is my predictive distribution for W. Now we already have the distribution for X from state space filter and Kalman from Kalman filter, and we use both of them in our observation model in order to predict Y. Once we predict Y, we use, now we have, for example, we have the data point available to us. As you saw, the first data point that was available. So we use the Gaussian conditional equations, which are been in theory for a long time, and we use them in order to update our posterior for X as well as the posterior for W. And once we do that, now we have the posterior for W. Now again, we'll use the Gaussian multiplicative approximation to obtain the posterior for W square, going back from W to W square. Now the main step is, how do we obtain the marginal distribution or the posterior for W2 bar, given that we now know the posterior for W square? We have shown in our paper that we can form the joint distribution between W square and W2 bar, and we can marginalize out W square in order to obtain the marginal distribution for f of W2 bar. And all the equations and proofs are provided in our paper. I don't want to go more into that part, but everything is provided in our paper if you want to have a look at it. Now, as you saw that we went in the forward path as well as in the backward path in order to obtain our posterior for W2 bar, which is expected value of W square. So we started with the prior, obtain our posterior. So this is what AGVI provides, that as we recursively see data points, we'll be able to infer what is our sigma square W value. Let's look at a quick verification. For example, the red line here shows the true sigma square value present. And this is our predictions, where the black line shows our prediction, how we are learning, and the violet region shows our uncertainty. You see that as we move through time, we do the online approach, we are able to converge to what is the correct value for the sigma square. We also did multiple tests in order to check if our method is theoretically correct, if all the proofs, everything are correct. So we did optimality test, we did consistency test for the uncertainty, which is basically the violet region for the predictions, as well as we show in our paper that our error variance estimates are unbiased. We also compared with two other competing approaches, which are both recent approaches. One is in the Bayesian category and one is not Bayesian, but it's in a correlation category. And we compared based on the metric RMSE, and we compared across different values of sigma square, starting from small to large, and we see that we are more accurate compared to the other two approaches. As well as if you look at the last column here for the time, you'll see that our approach, because of the analytical nature, we are more than 2 orders of magnitude faster than the competing Bayesian approach. And we are also faster compared to the correlation approach, which for now doesn't provide us uncertainty. So overall, AGVI is an online method that provides consistent estimates, accurate estimates, as well as we are way faster than the competing approaches. Now, till now we have looked at the univariate case. What about the multivariate case? What if I have more time series? For example, I have 2 time series with different variance terms, and we want to quantify each of the variance terms for this time series. Let's just remove the function and keep just the uncertainty that we want to model, which can be assumed to be 2 process error terms with Gaussian distribution with mean 0 and variances sigma 1 square, sigma 2 square. Now, if both of them are independent from each other, the joint distribution would look something like that. And then it becomes straightforward to evaluate, because we can just use univariate equations to obtain each of our sigma square value. It doesn't matter, we can scale to a large amount because they are not dependent on each other. But in practice, it might not be the case. We might have correlation between the W1 and W2, which are the process errors, as well as between many other process errors that you might have. So we need to evaluate also the covariances associated with W1 and W2. So the Q matrix would look something like this, where on the diagonal we have the variance terms, on the off diagonal we have the covariance term. Using AGVI, we can quantify the variance terms as well as we can do it for the covariance terms, and we can do it analytically in a closed form manner. Now, this is still a 2x2 matrix, right? Just one covariance term. What about higher dimension? Will it be able to scale to larger dimensions? For example, I am analyzing multiple time series, suppose n time series, and each of them has their own variance terms to evaluate. All right, so for example, I have n time series and I have n sigma square terms to evaluate. The Q matrix now will look something like that, where we'll have all the variances and we'll have all the covariances in the off diagonal terms. We see that the Q matrix becomes non-PSD, meaning that as the dimension increases, it's difficult to keep the Q matrix to be PSD because of numerical errors. in order the Q to be PSD, we want it to be symmetric as well as the eigenvalues need to be greater than equal to 0. So in order to do that, we rely on Solesky factorization. So we bring in Solesky factorization into our method. So a brief overview of what the Solesky factorization is. So in this case, we use an upper triangular matrix L. We do the transpose times L, and we end up with a PSD Q matrix. In our case, since all the elements of the Q matrix are random variables, as you saw from the variance and the covariance term, we do not have a deterministic matrix. We need to use an upper triangular random matrix because those elements also need to be random variables. For example, the upper triangular or the elements of the upper triangular random elements are given by this A, B, and C. And this is just plug and play of what the formula we saw before. We do transpose times the same L matrix, we get all these elements. Let's assume that A, B, and C are all Gaussian distributions. So we'll just input these values here. So this is the thing that we'll see. We'll see the square of Gaussian distribution, we'll see product of Gaussian distribution, as well as the summation of Gaussian distribution plus another square of Gaussian distribution. Now, we have seen before that we can do it analytically. We can use GMA in order to obtain this. So we already have what are the moments for all these terms, regardless of how big the size is, we can obtain all of the terms analytically. So this is basically what you do in the multivariate case. We do not build Q directly because of the possibility of non-PSD. We build it from upper triangular random matrix L. We obtain the posterior for L and use it in order to build the posterior for our Q matrix. Now, let's look at a quick example for inferring online inference for the full covariance matrix. Suppose I have a Q matrix of these values where there are some variance and covariance terms. For example, I want to infer this term variance which is equal to 2. And here is the result where the black line shows our predictions, the violet region shows our uncertainty. And we can see that starting from some vague prior knowledge, we are able to identify what is my correct value for the variance. And I can repeat this experiment for another variance term or covariance term, and the result is the same. We are able to identify what is the correct value for my variances or the covariances, and we can do it all analytically and we can do it online. Okay, so till now we've been dealing with something called the homoscedastic aleatory uncertainty. As you have seen that the shaded region is still constant. We do not see any pattern in the uncertainty. But in this section, I'm going to talk about an important phenomenon that we normally see while trying to model like practical phenomena, which is called the heteroscedasticity. For this, let's consider that we have this function. So we have a deterministic function g of x1 and x2, where x1 and x2 are both input covariates. And let's just rotate the plane just to view x1. So we keep the same diagram, we'll just rotate the plane in terms of x1 so that we do not see x2. Let's remove this plot over here in order to see the data, and you'll see this pattern. So you will see something strange, that the variability in the data is now dependent on what the input covariate value is. You see that we go from smaller to larger value depending on where I am on this axis. This phenomenon occurs because of lack of explanatory variables. As you see that we just like removed x2 and visualized it was there in the function, but we visualized in this way that x2 is not there. We do not know, we just have x1, and we'll be able to see that some of this uncertainty in data will vary depending on the input covariates. How do we solve it? So for this, we'll combine our AGVI approach with this neural network structure called TAGI. So we're going to use it in order to infer our sigma square V as a function of all the input covariates. And we combine the approach, we call it TAGI-V in order to do that. So before that, let's look at the architecture of TAGI. So we have the input covariates X, we'll have, because it's a neural network architecture, so we'll have all the hidden layers that has the hidden inputs, and then we have the observation Y, and we have, let's call it the predictive error that is connected through the observation model, which would represent the aleatory uncertainty in the data. And we have all the parameters between the layers, and we want to evaluate all of this. So in TAGI, we can analytically infer the theta and the z. So we can obtain the posterior for the theta and z without relying on back propagation. So we can do it much faster because of this, because of the computations. The limitation is that it was seen to be expensive to obtain the sigma square v because have to rely on either gradient-based approach or just simply grid searching across values in order to find. And this was it was computationally taxing in order to obtain, for example, larger data sets. It was really computationally demanding. And also one thing is that it cannot quantify heteroscedasticity because it assumes it to be homoscedastic and it would represent a constant variance. So we do a small change in the whole network. So we go from the input covariates to the last hidden layer, and then the z output. This remains the same. So only modification that we do is in the output layer, where we put v2 bar, where previously I showed that it was w2 bar. In this context, I represented by v2 bar, and this whole graphical model is same as AGVI, which is connected to the observation. Hence, there is only a minor modification that is required in the output layer, which makes the total complexity same as the AGI. So we are still with the same A square notation for the big O, where A represents the number of hidden units within each layer. So it's a square term, so it's still very computationally efficient method. Let's look at through a 1D toy problem where we have a function for the y and we have a function for the sigma square v related to the input covariate x. So the function in red, you see this is this equation here, and the uncertainty bound that you see, the red region, which is given by this equation here, sigma square v related to the input variates x, where now it changes based on the value of x. And we'll use this for this problem where we have two layers of hidden layers with 128 hidden units. On the output, we have z output and v2 bar, and then connected to y. Now, when we'll do our first epoch, meaning we have seen all the observations in the dataset once, we see that we do not learn much from this whole setup. So we do not, neither we learn the model nor the uncertainty. But as we'll see the observations repeatedly, for example, for 4 epochs, meaning that we have seen the entire data set 4 times now, we are able to, like, we are going towards what is the correct value for the prediction model as well as for the uncertainty. As well as you can see that the log likelihood value is increasing. And finally, by epoch 28, where we converge, you see that we have correctly identified what is our model, as well as we are able to identify what is the uncertainty associated, which represented had a function with respect to the input covariates. We also did multiple tests regarding other toy problems, 1D problems, and also did with small UCI regression problems. But here I want to focus on the large UCI regression benchmark because it needed a much larger neural network that had like more than 1 million parameters. So it's basically a computationally demanding task to run. And we compare it with various other methods from like that are published in reputed journals in computer science. And we see that based on the metric log likelihood, we are able to beat most of the methods in like 4 of this large regression benchmark. So we are saying that we are better in terms of log likelihood as in comparison to all these methods. So finally, in conclusion, AGVI, which is the approximate Gaussian variance inference, we can do it analytically and we can do online inference using it. We can use it to evaluate the full covariance metrics. The method provides accurate, consistent, and fast computations. And finally, all the code is available on GitHub using this link if you want to use it in your project. That's it. Thank you.
Thanks for the really interesting talk.
Thank you.
By using AGVI, you're supposing that your aleatory error is symmetric, right, by default, because you're using Gaussians. Do you think this would be generalizable to asymmetric aleatory error?
For now, no, because we rely, actually the Gaussian distribution helps us to have that analytical tractability. You know, if we are not able to right now handle asymmetric distribution so that we can still handle the asymmetric while doing it analytically. For now, that is a limitation. We are restricted to have the Gaussian approximation, even though it performs really well, but we want to go there in the future. That we want to handle different types of distributions, and yeah, this would be something for the future.
Because I guess obtaining closed forms is probably a lot more difficult.
Yes, it's just to obtain, I mean, for if you can somehow find a link with Gaussian distribution, all the integrals are closed form. If not, you have to use numerical approximations in order to do that. That makes computation really much expensive. And if you want to do it for large, for example, if you want to handle like, I don't know, 400, 500 time series with all of them having their elitary uncertainty that you want to quantify, it will be really computationally tasking. So I know it should be, we want to go there, where we want to able to handle any form, not any form, but at least like the family of distributions, still asymmetric, but the math behind it is still there. But yes, for now, it is not possible.
Okay, thanks.
Thank you.
Thank you very much for a very interesting talk. So I was just wondering, okay, so if I understand correctly, you were approximating the square of the Gaussian distribution again by a Gaussian distribution. However, it will be a chi-square, right?
Yes.
So, and I also understand you are doing it because you want to stay in the Gaussian world because everything becomes very simple. It's a conjugate distribution. But the question is that how good is the approximation, because the chi-square distribution is very right tail, right? I mean, like it's like goes like in the tail, it's like right tail is very skewed, right? So how do you verify this approximation?
I mean, it's a really good question. This question we have been trying to answer for a long time, because you're right, we want to stay with the Gaussian distributions, and we do approximate kind of a chi-square distribution as a Gaussian distribution. But mostly from our empirics, we see that we are fairly accurate, even though I can understand in certain domain of the prior knowledge, the chi-square, the actual distribution being chi-square would be really effective. But if you are in the positive domain, I think it still can be approximated as a Gaussian. The approximation becomes better, but if you are much closer to the zero because of the positive domain, there might be issue in the assumption. So for now, I'm not sure to answer this, but from all our empirical studies that we have conducted, because we are not sure how it will perform in different problems, so we wanted to see how it performs on like regression problems, on time series problems, in order to validate at least if we are able to get good results. But for sure, this is a very good point, that in certain domains, it might be, the approximation might not be correct.
Okay, thank you.
Any other questions in the space or online? Okay, well, thank you again.
Thank you.
We are going to take a brief lunch break. We will be back at 1:30 to hear from the rest of the presenters. So thank you for joining us, and we'll see you then.
Welcome back. So we'll start this afternoon with a talk by Laetitia Jean-Collat.
Thank you. Good afternoon, everyone. So I'm Laetitia Jean-Collat. I'm a postdoc here at Concordia University. And I'm going to present the main topic of my postdoc, which is the understanding of Alzheimer's disease, analyzing especially a particular sequence of MRI, which is the ASL sequence, which gives information on how the blood perfuse the brain, how the blood diffuse within the brain, and how it's modified at the beginning of the disease. First, a little introduction about this disease. So it was named 100 years ago when it was discovered by Dr. Alois Alzheimer. It's the most common neurodegenerative disease in the world, and it's the cause of more than 60% of the cases of dementia, and it affects more people over a certain age, and 23% of the people over 80. The symptoms are globally characterized by a memory loss. So it's memory loss. There are different types of memory, episodic and semantic. So, but Alzheimer's disease affects all the kinds of memory. So episodic is more related to the memory of the event in our life, and semantic is more the memory of the meaning of the things. It also has some involves some language impairment, disorientation, executive functions problem, behavior also, and psychiatric changes with disinhibition, for example, and also some movement coordination disruption. And unfortunately, it goes gradually, and at the end, it leads to an inability to perform the simplest task. So it leads to a complete dependency. So how does it work in the brain? What do we know about Alzheimer modification in the brain? So it's a disease that affects proteins. The name is proteopathy. And two proteins are changed, are modified in Alzheimer's disease, two main types of protein, the amyloid, beta amyloid protein and the tau protein. So both have different roles. The amyloid plaque normally degrade naturally in the brain, and they are outside the neurons. And in the context of Alzheimer, they are abnormally folded, so the geometry change, and this change in the geometry of this protein leads to an accumulation between of the protein between the neurons, so a formation of plaques. And regarding tau, it has the protein tau usually has a role. Does it work? Yeah, has a role here in the consolidating the microtubules. So it helps. It's like a tape. It helps it has a role in the skeleton of the neurons in the axon. And in Alzheimer's disease, they are hyperphosphorylated, so they will disintegrate from these microtubules, and they will also form plaques, different kind of plaques, which are called neurofibrillary tangles. So these are the two main characteristics of Alzheimer, and based on that, based on this observation, it's the only way to detect, to pose a definite diagnosis of Alzheimer, and it can only be done post-mortem. So we can't give a definite diagnostic when the patient is alive. We can give probable diagnostic, but not definite diagnostic. And so when we observe postmortem with an histology, when we observe those plaques in the temporal lobe, it's a part of the brain, we can pose a diagnostic of Alzheimer's. So these two phenomena don't appear at the same time in the evolution. The first to appear are the amyloid plaque. So they are it's the first physiological symptom that appear in Alzheimer. Then it's followed by the abnormal tangles, and then, and only then, a modification in brain structure with a hypertrophy of the hippocampus, for example, and we can observe the first symptom, the cognitive symptom. So the symptom usually appear like 20 years after the first changes in the brain. So that is very important to be able to detect Alzheimer early before symptoms. Because once the symptoms are here, so when the person complains about its memory and the cognitive assessment shows that there is a deficit in cognition, it's already too late. Too late to test new treatment. So late for any solution and any cure. Even if we don't have today cure for Alzheimer's disease, it's important to be able to early in order to test potential treatment, to test potential molecule, to see if they can either slow down or stop the evolution of Alzheimer before reversible damage in the brain. So, and what we don't really understand is the initial cause. What leads to this is in the different proteins, and also how it propagates. So the underlying mechanism of Alzheimer propagation. We know where it propagates, but we don't really know how and why. So, many studies have shown that metabolism change in Alzheimer's. So metabolism is, for example, the FDG metabolism is how the brain consumes the glucose. So the consumption of the glucose change in Alzheimer's, and it's reduced in certain parts of the brains, and the reduction starts in regions that are called default mode network. So it's regions that are activated normally when we do nothing. So that's why it's a default mode network. We know that start in Alzheimer's to decrease in those regions. So this is with PET, which is a type of imaging scan. Now, regarding the cerebral perfusion, so it's the blood, the definition of that is the blood delivery to the brain. There are different neuroimaging techniques to assess that. For example, MRI, ASL, the one that I used, PET, NIRS, different kind of imaging. And globally, these techniques and the research on the perfusion changes in Alzheimer showed globally at the MCI, so it's a mild cognitive impairment, so it's the beginning of Alzheimer symptoms. There is hyperperfusion, so the blood delivery is lower than the normal. And it's, they say, this is a meta-analysis that we can show on. So it's most in the same default mode network that we just saw. And also, some studies have shown an attenuated neurovascular coupling, but only in mice. There is no study in human. So what is a neurovascular coupling is the capability of the perfusion to change, to be increased during the task. Because here the hypoperfusion is during the rest, but what happened during the task? Normally, certain parts of the brain are activated during this task, and when they are activated, they provoke electric signal, and they need oxygen the neuron need oxygen to work, and for that The oxygen need to arrive, and how the oxygen arrives in the brain with the blood. So the blood will come in more quantity during a task in the regions that are activated during the task. And this relationship between the neuron activity and the increase of perfusion is what we call neurovascular coupling. And one of the things that I've studied and that haven't been studied in Alzheimer at the beginning of the early stage is this neurovascular coupling. So this was for Alzheimer. Now, what is, if we focus on the period before Alzheimer, so before is detected, so more at risk Alzheimer people. So not very few studies have studied at this stage, and of them is there a problem with the microphone? Impression that it is on, something is off. Okay. Hope you hear well. So globally there is consensus. Mm-hmm.
Do you mind if I take that?
Yeah, sure.
Sorry about that interruption.
Does it work better? Oh yeah, I think it works better. So at the early stage of Alzheimer's, there is no consensus. So some show that there is no differences in the perfusion, and others some there is that there is some hyperperfusion, and others shows hyperperfusion in some regions. So we don't really know, and moreover, they didn't analyze the activation of the perfusion, so the task-related change of the perfusion. And neither the relationship with the other neuroimaging modalities. So the protocol in which my studies take place is a protocol which objective is to better understand the neural mechanism at Alzheimer onset. So we have more than 300 subjects with subjective memory loss, but normal cognitive assessment. So it's just that patients that came to the hospital to have the point of view of a neurologist because they had memory loss, but the cognitive tests were normal. Nevertheless, they usually are considered as at risk of Alzheimer's disease because usually people notice before slight changes before it can be seen by doctors. So this population is considered as risk of Alzheimer's disease, and among this population, a part of them already have amyloid plaques because they have also these participants perform different neuroimaging scans. One of them is a PET amyloid to see the amyloid plaque I talked about before. And so a part of this population already has the amyloid plaque. So we will call them amyloid positive, and they are really at the beginning of the Alzheimer process. So what I did is to compare this population with a population without amyloid plaque to understand once the amyloid cascade, once the Alzheimer event have started in the brain, what happened regarding the perfusion. So I will go quickly about the neuroimaging techniques that I use. So it's arterial spill labeling. So it's an MRI sequence that permits to assess the quantity of cerebral blood flow per regions, per voxel in the brain. So these are some characteristics on this sequence. So at the end, we had to check the data quality of every participant, and at the end we had 281 subjects that performed correctly this ASL sequence. So what was the method that I used? So the data that we have is a magnetic field generated by the brain and in response to a stimulation. So this is the principle of the MRI. And this gives information about in a normal MRI about the different tissues. And in our case, as we are in the context of ASL, so one volume out of two is labeled, so have a spin inversion. So if we take a first regressor with just the alternation of 1 minus 1, we have here the first explanatory vector of our model is a perfusion baseline. The second one is a bold variation, so it's how the magnetic field, how the data evolve with the task due to the oxygenation. And the third one is the interaction between both. So it's the perfusion activation, is how much this perfusion will increase during the task or decrease, we never know. And in our GLM, we added 6 motion expiratory variables to really remove all the confounding factors. And the second level analysis consisted in a two-way ANOVA. With 2 factors, so amyloid and sex, because we wasn't sure if the sex didn't have an effect on how the disease impact the perfusion. So we also included the interaction in the model. And as we did one test per voxel, and there are millions of voxel in the brain, we needed to do a multiple testing correction. So we did a cluster correction with a p-value lower than 0.001, and then a correction for the clusters that are the cluster identified with Gaussian random fields theory correction. So here are the perfusion baseline result that we have. So this is globally what happens in the brain during the rest. Because, yeah, what I didn't detail is that when they are in the MRI during this sequence, they have a task to do. Well, not to do, but they have a task. They have a checkerboard that a flashing checkerboard, so it's a visual stimulation during 1 minute, in alternation of black screen during 1 minute. And all of this during 10 minutes. So this why, by the way, the board has this, the second vector has this shape, is because there is one activation, stimulation, visual stimulation during 1 minute, then one black screen, etc. So if we look at the baseline, perfusion baseline, the Z statistic corresponding to this explanatory variable, what do we have if we compare this contrast, this estimated coefficient, if we compare it between amyloid positive and amyloid negative, what do we have? So globally, we can see that during the baseline, during the rest, during the black screen, we have an hypoperfusion of, this is the blue, all the blue part of the brain. So an hypoperfusion in different regions that, interestingly, correspond also to the default mode networks, most of them. And so I put in gray the ones that didn't resist the cluster correction, but are still significant with a p-value lower than 0.001, because some of these regions are really interesting and in line with what we could expect. Also, we have in the default mode network an hyperperfusion in the hippocampus and the para-hippocampal gyrus. So it's 2 different phenomena in the same default, in the same network. And we also have changes in the visual network with hyperperfusion in the occipital. So the occipital is this part, the posterior part of the brain. So hyperperfusion in this part, and also the occipitotemporal part of the brain, and hyperperfusion in the northern part of the brain, which is here in red. So it's the fusiform gyrus, which we know also that is impacted early in Alzheimer's disease with the hippocampus. So this has an hyperperfusion the same thing for the hippocampus. So this is quite interesting because yeah, we see that globally there is an hypoperfusion, except in the regions that are known to be to contain many amyloid plaque quite early in the process of Alzheimer degradation. And why do we have the visual network here, whereas it's the baseline? So whereas it should be at rest, I think we think that it's because of retina persistence, because when you have something that flash a visual stimulation during 1 minute, you still can see this image, even if the image is not here anymore. So this is a residual of activity of the visual activity. But it's quite interesting to see that, with even if it's just a persistence of this visual stimulation, so which is at a lower level, we have an hypoperfusion in this brain, in these regions. And now if we look at the interaction between amyloid and sex, we have many parts with a significant, after cluster correction, significant interaction effect. So globally, the hypoperfusion that we saw is globally more severe in men. And regarding the hyperperfusion, it depends of the region. In the intracalcarine and fusiform, it's more pronounced in women, and in the hippocampus, it's more pronounced in men. So it's important to take, it was important to take into account the sex in the analysis. Now, regarding the impact of the task, so when the checkerboard flashes, so what happened? If we just look at the main effects, the mean effect within each group. So we don't compare the group, we look at within the amyloid positive, within the amyloid negative, and we separated male and female just for the visualization. What we see is that there is most of the activation is in the occipital part of the brain, which is the part that we know to be mainly responsible of the visual process. So it's logical that when we see something, it activates this part. So more blood comes into this part. So this is what, just to reassure us that the protocol was done correctly. It's not interesting per se, but it was a verification. It's always important in MRI analysis to do many verification. So when we compare now the two groups, the amyloid positive and amyloid negative, so the perfusion changes related to the task, and we compared these perfusion changes between the two groups. What do we have? We have, so we don't have any significant effect after the cluster correction, but we still have interesting effect with a uncorrected threshold of 0.01, with a decrease of the perfusion changes in the hippocampus, mostly in men. So hippocampus here, that we can see here, in the insula, that we can see here and here, and also in the left lateral occipital superior. And also in the frontal medial orbital, but we don't see here. It's not in the plane that we kept. So what does it mean? So actually, can it be explained by two phenomena? Regarding the hippocampus, we had an hyperperfusion of the hippocampus, but during the task, we lose this hyperperfusion. Actually, just the level of perfusion in the hippocampus reach the normal level during the task. So we could assume that maybe during the task, as it's a visual task, there is not enough energy in the brain to feed the hippocampus, the hyperactivity of the hippocampus anymore, because all of the energy is focused in the occipital part, in the parts that are supposed to process the visual information. So what we can have as a hypothesis is that maybe the well, it's one of the interpretation. It's the increase of activity, the hyperperfusion that we saw at rest, in the hippocampus. Maybe it's a compensatory effect, and which is lost during the task because there is no energy for every part of the brain during a task. And also, but there is another effect. So here, here it's not the same interpretation at all, because these are the parts that are normally increased during the task. So because that are the parts of the brain that deal with the visual stimuli. So what we observe is that it's increased in the amyloid negative, so the control group. It's also increased in the amyloid positive group, but at a lower level. So it's as if the neurovascular coupling was reduced, because it's the energy, the activity, neural activity don't imply enough increase of blood arrival in this part of the brain. So this is an evidence of a reduction of neurovascular coupling. And we also have, but we don't see it because it's not in the plane of the cut, but we also have a cluster where the amyloid positive changes are increased compared to the amyloid negative in fusiform calcarine and in other parts of the brain. So to conclude, we have obtained different things. So the cognitively unimpaired amyloid positive perfusion can be characterized by different aspects. So if we look at the baseline, perfusion baseline, so during rest, we have mainly hypoperfusion, and mostly in the default mode network, which is coherent with the metabolism aspects that we know in the literature, so the reduction of glucose consumption. And also we saw an hypoperfusion in the visual network. And we observe an hypoperfusion in the hippocampus on fusiform, so which may be compensatory effect. And during the task, we show that there is an increase of the perfusion in the occipital lobe, but weaker in the amyloid positive group, so which show reduced neurovascular coupling. And so globally, we observe perfusion modifications in cognitively unimpaired amyloid positive group at rest and during the task. And interestingly, this modification are sex dependent, so which is new result. So we can conclude that the vascular dysfunction plays a crucial role in the pathogenesis of Alzheimer's disease and should be included in Alzheimer's disease research framework for early detection. And what's next? In the future months, I will work on the understanding of the role of the perfusion modification in the Alzheimer's pathogenesis, because we know that it has a role now, but we don't know if it's a causal role or a consequence role of some event, because this perfusion change could be the consequence of the amyloid plaques, for example, but it could also occur before the apparition of amyloid. So it could have led to the amyloid abnormal plaque. So for that, we are going to correlate this result with the PET metabolism, PET FDG, and the PET amyloid. And we also are going to study the longitudinal evolution, because all of these data, we have them for every patient during 5 years. So we can look at the evolution, so how it worsened, and compare also how if it worsened faster than the amyloid accumulation or the opposite. And the other thing that we are going to do is to implement, to add the perfusion analysis in a context of Alzheimer's detection, because the first part was for Alzheimer's understanding, but we also need to be able to work on the Alzheimer's detection. So we will see if this perfusion allow a prediction of the MMSE. The MMSE is a cognitive score. So if it can predict the MMSE at present, so at the same time, and if it can predict the future decline also with the longitudinal data that we have. And because we know that PET can a bit have a little predictive power of the cognitive score. So we will see if we add the ASL, so the perfusion, if it improves this prediction power. So that's it. Thank you for your attention, and I'm open to any question.
I do have a very general question. So this is really not my area of research, but my question is more, do you have data where you had patients who you could diagnose, who passed away and had the disease, and you have where you sort of maybe information which could help, you know, in these?
We don't have that in our database, but there are several public databases that exist, so that we can also use with longitudinal MRI, and going through the end of the longitudinal analysis, so through until the death, and with the Alzheimer certification at the end. So we could use those public data set for comparison, but we have to be careful because as it's not our data set, that means that the MRI would have been acquired in another center with different parameters. And for this kind of multicentric analysis, it's always a bit dangerous because of confounding effect due to the center, due to the way the data have been acquired. So we could compare, but not now. Now we will maybe maybe later when we have finished this analysis, we will have a look on the public data set.
So now the conclusions are all for at risk.
Yeah,
patients.
well, it's even a little more than at risk because the population with cognitive complaints and plaque amyloid, they are a bit more than at risk. They are at the really early stage of Alzheimer. It's 95% of them will develop Alzheimer. Maybe not 100, but yeah, more than 95%.
Okay. Thank you. Any questions in the audience? Ohana.
Sorry, I might have missed the part where you talk about what the model that he used for concluding that the perfusion is sex dependent. Can you explain a little bit more?
Yeah, it's a higher level model. So the first level model allow to have an estimate of the importance of each explanatory vector on one of these in the perfusion baseline, on the other in the interaction. And based on the importance of these vectors in the explanation of the variance of the data, we can compare these coefficients within a higher level analysis, so within an ANOVA. So it's a two-way ANOVA, including ANOVA it's an analysis of variance. So it's another kind of linear model, of general linear model, but with a label and not continuous variable label for each factors. So in this model, higher level model, we have 3 explanatory variables. So 4 explanatory variables. We have the constant. So we try to see if the data can be explained by a constant, by factors with the amyloid label, so yes or no, and a factor with sex, and an interaction factor. So it's really the multiplication of the 2 first factors. And if this regressor has a significant role in the model, so for this we compare a model with it and without it with Fisher test. So if it improves significantly the explanation, the the explanation of the variance of the model, we consider that in this part of the brain, when we have calculated it, where we consider that the interaction is significant.
Okay, thank you.
Thank you very much, Lucia. So thanks, and we will, we will now have Roxane Turcotte.
So hi everyone, I'm Roxane, and the work I'm presenting today is part of my PhD thesis because I just defended my thesis 3 weeks ago. So the work I'm presenting today is about semi-parametric modeling and longitudinal modeling of risk exposure for car insurance. And the particularity of this, this work is that it includes monotonicity constraints on splines for the evaluation of kilometers as a risk exposure. Okay, so this is not working. Okay, so I can't advance the slide. I don't know, if I click here, it's not moving, and if I click here, it's not moving either. Okay, thank you. Okay, so I was here. So for those of you who are not familiar with car insurance, the rate making is usually done by using proxy variables such as gender, the age of the drivers, their level of education or marital status to establish the tarification. And by doing so, what the insurers are doing is that they're finding in which group of the society the riskier behaviors are, but they don't actually identify what are those riskier behavior, and more importantly, whose drivers are more or riskier. So processing GPS collected data has the advantage of to obtain reliable information about the behaviors of drivers and has the potential to replace those proxy variables. One of information that is directly related to the risk is the distance traveled, and the relevance of this variable for car insurance have been studied before, and it is relevant because insurers, policyholders are not good at estimating what their annual kilometers are at the beginning of the contract when the question is asked by the insurers. We are looking at this problem also because pricing according to the kilometers driven has the advantage that it can generate several benefits for society by encouraging a reduction of the car usage. And so
I've listed here some benefits. So for the environment, for health, encouraging to use active way of moving themselves, and resource management, so electricity or gas. Also setting the premiums on parameters that the insured can control as a positive effect, that it can encourage positive change of a habit, because someone can change easily their level of education or their marital status, but they can change easily to use their car less. So in this work, the coverage studied is the collision coverage, because mileage is the primary source of exposure to risk for this coverage, as opposed to theft, where the mileage has little or to no link with the risk. And all the numerical results are from Canadian data from personal lines. So just to be on the same page before jumping into the results, I like to present the main concepts that are used throughout the presentation. So we all know a GLM can estimate a model, can estimate the location parameter with a link function and covariates. If we include non-parametric term into the modeling of lambda, then we get a generalized additive model. But if we want to use that kind of modeling with distribution that are not part of the exponential family, we can use the generalized additive model for location, scale, and shape. And this is the framework I'm using to estimate the models, because the longitudinal models that I'm using are not part of the exponential family. So the non-parametric terms that I'm using are splines, so smoothing functions that are defined by polynomial pieces. And what is important to use those smooth functions with gamma LSS is that it can be written in a linear combination of basis function and parameters beta. The spline that I'm using in the first part of the presentation is a B-spline. So here we have its most widespread in the literature, its definition that is most widespread in the literature, which is its recursive definition. And well, I just wanted to present it. So the starting point for claim count analysis usually is a Poisson model, and usually we are using duration as the exposure measure for the risk, which means that if an insured will cancel their contract midterm, then they will get back half of their premium. But what we're trying to do here is to introduce the kilometer in the same proportional way as duration in the modeling of the location parameter, but we also include splines on both the kilometers and duration to analyze what is the real, what is the relationship between the risk and those exposure measures. So we estimated the GAM-Poisson model, and for the kilometers driven, we see that we've got like a parabola shape, so a stabilization around 40,000 kilometers, and then it decreases. The problem with that kind of model is that it does not tell you how the risk evolves if someone that usually drives 40,000 kilometers decides to drive more kilometers. What is happening here is that the types of drivers that are from the lower quantile of the distribution are not the same type of drivers that are in the upper part of the distribution. So the slope might change, but it should always be increasing, because the risk is always greater when you drive more kilometers. How we explain this result is that because the Poisson model does not have a longitudinal component, so there's a lot of residual individual heterogeneity in the model. So we are using fixed effect and random effect to introduce the longitudinal dependency in the Poisson model. So in the random effect model, we define that the response variable are conditionally independent, and the random effect is following a prior distribution that is a gamma distribution of mean 1 and variance 1 on nu. And so by choosing a Poisson gamma, then the expression of the joint distribution is closed. So a long history is not making the model more complicated to estimate. And yeah, the distribution has a name. It's named the multivariate negative binomial because it is widespread in the actuarial literature. And it is not a member of the linear exponential family, so we are using gamma LSS to estimate the model. So here's the estimated spline. So compared to the first model, there is an improvement because the decreasing starts from 60,000 kilometers and upward, but here the observation are really scarce when the decrease begins. But this is not perfect, so we're looking at the fixed effect model. The fixed effect model and the random effect model are linked because if we're looking at their first order equation, we see that if nu is null, then the first order equation of both of these models is the same if nu is not null. So the estimation of the fixed effect model shows that the distance driven is almost linearly related to the risks. So in the point of view of using this measure, using this variable for an exposure measure, this is really interesting that we get an almost linear relationship. We only have a slight deviation at the end of the distribution, but the observation is scarce at that point, and the relation is increasing, so it's okay. So which effect should be used in practice? So the fixed effect is more general because in the random effect model, we assume that the random effect distribution is independent from covariates, which is not verified in practice, even though it's a typical assumption in actuarial science. But even though if the fixed effect model is theoretically better, it is not suitable for pricing because we have a problem if you want to price new insureds because we have to estimate a parameter for them, and there's a lot of parameters to estimate in that model. But it teaches us that the relationship between millage in risk is marginally increasing and almost linear. So even though the fixed effect, the random effect has their drawbacks, we are still using it because it's better for pricing because it's flexible, but we have to correct certain things. So, so our goal is to use a model that is can be used in practice, but also has a logical relationship between millage and risks. Because there's a lot of advantage to using a longitudinal model, and there's a lot of advantage of using kilometers as the exposure measure. So we correct the model by using monotonicity constraints, and here we are looking at a wider range of spline, P-spline, cubic regression spline, and thin plate regression spline. And we study the impact of these constraints on the premium structure according to different claim histories. So I've just put a recall about the MVNB. What I wanted to point out is that by choosing mean 1 for the distribution of the random effect, we have that the expectation of n is unchanged, it's still lambda. So because we want to do rate making, we are looking at the predictive distribution. The predictive distribution of an MVNB is simply a negative binomial with this expectation. So because the expectation is, the a priori expectation is simply lambda, then in the predictive expectation, this term here acts as a correction factor between what really happened, so the sum of the claims that occurs, and what the model predicted, so the summation of the past expectation. So if there's more claim than what the model expected, this factor is greater than 1, and the premium is higher. So that's a recall of the B-spline definition, the definition of the B-spline. What I wanted to point out is that the B-spline has local basis function, so they are non-null strictly around their, the basis function are non-null only around their knots. They're not. And because of that property, it's easy to put the monotonicity constraint on this spline. We simply have to ensure that the parameters of the spline form an increasing sequence. One way to do this without using optimization with constraint is to define the parameters gamma of the spline as a summation of beta parameters that are unconstrained, and we ensure that it's an increasing sequence by using the exponential of the beta. So those gamma parameters are the ones that are in the spline. What is important here is that using that kind of parameterization could make convergence difficult to achieve because there are a lot of the beta 1 here interfere in the estimation of several gamma parameters, and then like the later gamma parameters are estimated using an increasing number of exponential beta parameters. So we estimated that model. So this one is the same as we saw before, that a decrease that starts around 60,000 kilometers, and the monotonicity constraint flatten the end of the distribution, but it also flattens out the spline for the duration, meaning that in that model, like the model decided, the data decided that only the kilometers driven were driving the level premium in this case. The other spline that we are looking at is the cubic regression spline. So it is so this is its basis function, and they are obtained by using the assumption that the second derivative of the spline varies linearly in each interval, and then we integrate twice, and we get this definition for the spline. And we're using cubic spline because it's compromised between smoothness and fit to the data. Those basis functions are not local as the one before, and we found out that the fact that the basis function are non-local is enough to get rid of the decreasing even in the unconstrained model. So here, those two splines are alike. But if we impose monotonicity on both splines, like before, it flattens out the spline of the duration. By using a non-locally defined spline, we are able to correct the spline over its entire domain because the correlation between millage and other driving habits is a phenomenon that affects data across the entire domain. And also, we had a problem at the tail of the distribution because the observation was scarce. But so like a local spline, a local basis function can generate a local overfitting. The last spline we're looking at is the TPRS, so the thin plate regression spline. It's a spline that is considered like an ideal smoother by many research because it's more general than the other two. Those basis functions are not local, like the cubic regression spline. And to ensure monotonicity when we don't know the characteristics of the function, one easy way to ensure monotonicity is to go numerically and just to evaluate the derivative over several points, and then use the derivative over all those points as constraints to impose monotonicity. So again, the splines are the basis function are non-local, so the spline is always increasing, even though there are no monotonicity constraint. But in this model, we see that the duration is not flattened out. So we both the distance and duration drive the level of the premium in this model. So obviously, if the best estimate was the model without constraint, it would be, with constraint, if monotonicity was yielding the best statistic, it's the one that would be yielded by the model without constraints. So we have the best in-sample statistics for the model without constraints. But what's interesting is that the difference between without constraint and with constraints are very less important in the out of sample. Another thing that is interesting is that by including the exact kilometers that was traveled by the car in the modelization, we found that gender is no longer a significant variable in the model, so we can remove it from the modeling. However, marital status is still significant, so we have to look at other telematics data to try to replace, to capture what this variable is capturing. And this is a result that was obtained by 2 other research work. So we are giving another argument for that. And lastly, we're looking at the premium structure in function of the millage. So for the different splines, so we have the cubic spline and the P-spline. There's only one line for each because we saw that like the spline for the duration is flattened out, so it doesn't interfere in the level of the premium. So we see that those 2 models are basically the same for 40,000 kilometers and less. And this is where most of our answers are. So those models are basically similar. For the TPRS, we see that if the insured stays the whole year, then the level of the premium is generally higher than for the other 2 models. And we also see that the 2 curves of the TPRS models are growing apart. So this means that someone who drives more kilometers has a less rapid premium augmentation with this model. And that can be surprising at first, but if we are thinking about it, if you are driving a lot of kilometers in a short time, then you use highways a lot more, and highways are considered safer roads because they are it's one way, there's no crossroad, there's no pedestrian, there's no cyclist. So as opposed to if you're driving not many kilometers, so it doesn't really matter if you're driving them in 6 months or 1 year. If you drive something like a couple of hundreds of kilometers, mostly you're doing city driving, which is riskier. So the risk profiles are more similar in the lower tail of the distribution. Now we're looking at the evolution of the premium according to claim history. So in black, that's the a priori expectation. And then we have how the premium evolves if we have 2 claims in 2 years, and how the premium evolve evolves if we have no claims in 2 years. So we see that if we have no claims in 2 years, we don't have a substantial bonus in the if we drive not many kilometers. So we can explain this in 2 ways. So first, if we drive not many kilometers, then we can consider that the driver has not been observed enough to grant them a bonus. But we can also look at the definition of the predictive expectation. So if this driver doesn't drive a lot, then the model predicted a little expectation. So if there is no claim, then this is what the model predicted, so there is no bonus. But on the other hand, if we are looking at the malus curve, there's a premium augmentation right away from the very first kilometer, because if the driver is driving little kilometers and still have claims, this is not what the model predicted, so there's a premium augmentation. And another characteristic of this curve is that it is steeper, like the malus curve is steeper than the a priori curve, meaning that their premium increase more rapidly. And this is a desirable characteristic because this discourages what we consider bad risks to expose themselves excessively to risks. And in conclusion, we have studied different longitudinal and semi-parametric frequency model to include the distance driven in rate making. We have used random effect models because they can introduce longitudinal dependence and they are practical, they can be used in practice, and their closed form allows us to have a long history without complication in the modeling. But there was some inconsistency, so we looked at different spline and put monotonicity constraint to correct those irregularities. And it is relevant to do this because using kilometers driven respect privacy of the insured, because we do not consider when those kilometers were driven and we don't consider where they go. So this is important nowadays. And we said that gender is not significant by including millage, but we have more research to do about telematics data to replace the other discriminatory covariates that are still significant. So that was it.
Merci. How do you explain or how do you take into account the correlation between distance driven and number of kilometers? Because you consider both. Hello?
Yeah, the kilometers, driven, but I didn't understand the other one.
Duration.
Duration and okay.
Yeah. So because you would maybe wind up double counting, right?
Yes. So like there was a research that put like tensor product with those two to try to do like that, to introduce the correlation between the two, but that was not practical for pricing. Like the curve was not interpretable for pricing. Okay. So sure, there are like there's like a correlation because like the longer distance are associated with the longer duration, but like we tested out like the independent case before, and like when we put monotonicity, we see that it flattens out the duration. So like duration is like no longer in the model.
Yeah, so it becomes kind of a constant factor.
Yeah, exactly. So so yeah, that was like a first step because like the like the dependence with the duration and kilometers is like complex. So like if the easy case of a tensor product was tried and not practical, and then I did the independent one and see that I think because I continued working on this, so like for the collision coverage, like duration is not that important. So instead of trying to modelize the dependence within the two, I would rather just remove duration for a collision coverage.
Yeah.
Yeah.
Okay. That answers my question. Thanks.
Okay, you chose for your x-axis the distance. So my first question is the distance over a 1 year period or it's cumulative or something? That's my first question. Because, I mean, the insurance company sets your premium from year to year.
Yeah.
And, you know, from 1 year to the other, or from 1 year to another year, you know, factors could change. So my first question is that distance, is that over 1 year or is that cumulative over your lifetime?
No, it's for 1 year. So like everything is changing from year to year. So some models assume that your covariates just stay the same, but not in this model because like they use the simplification because it like the model is easier to estimate. So like, but we didn't do that. We like everything is changing from 1 year to the other. So if your covariates are changing, like you move, or if you drive less, then the model is changing according to what your situation is that year.
But normally an insurance company would set your premium before you actually do the driving. So if you start like fresh, like the next year kind of thing, they don't know how much mileage you're going to be driving.
Yeah, but the thing is that what we're trying to do is like a price, because now there's research and then there's regulation. So what we're trying to do is like get the price per kilometer. So you will pay a premium according to that number of kilometers, and then that's the model we're trying to do. After that, there's regulation that you cannot pay more after you pay, but that's another thing. Like regulation will not allow for a premium augmentation because it's based on duration. Like you pay a contract for 1 year, but if you would pay a contract for a certain number of kilometers, then you will have to get a new contract when you reach that number of kilometers. So yeah.
So is this like your research is like a proposal on how to like charge?
Yeah, but
premium?
that's the thing. Yeah, because that's the thing. Like kilometers are really useful to get rid of like identifying the riskier behavior instead of just using gender, like to determine who drives more than what they claim to their insurer. So that's why we are looking at this. But after that, if we want to propose a model, there's need to be statistical evidence, like if we want to change the regulation. So that's what we're trying to do, to get statistical evidence and to really get a hold on how kilometers affect the risk, to then eventually propose a model. And like with the insurer, we're working with an insurer. The data comes from an insurer. So like we're discussing that kind of things of what we find in research and how it can be implemented in practice. Like it's part of the discussion. It's not the whole research. Like I'm doing my things, and then I talk to them, and we have discussion about like to get ideas of where I could go that could be usable and practical. Yeah.
Just a final question. So the x-axis, you chose distance, but why? I mean, there's a lot of different factors that could influence the premium.
Yes.
Like, I mean, so why did you choose distance and not another factor?
Why I choose distance? Yeah. Because it's between there's many data that are collected by the GPS in the GPS machine in the car, but like the distance travel is like the easiest one to process, because like there's the speed, the deceleration, acceleration, what else? Like there's many covariates, that there are many variables that are collected by the telematic device in the car, but like in the first step, like the distance travel is the easiest one, and there are evidence that it is beneficial to use that instead of gender. So so there's an interest. So, and there's things that we don't know how to use to process it in the model, how to use it in the model. So that's why we use that that covariate, because using telematics data in tarification, they're like you could not, like just last year, I think in Ontario, you could not increase the premium based on telematics data. So that's a new thing, that you could really set the premium according to how the driver is driving, according to the telematics data. So this being a new thing, that you can really increase the premium based on how they drive. What I was going with this.
But you know, the GPS doesn't pick up factors like maybe somebody's on medication or somebody.
No, it's just
or
like
lack of
how the
sleep
driver,
or whatever.
yeah, how the car is moving.
Yeah, but if that becomes a big risk factor.
Yeah, but that's it. The
But is it the
use
best
level of
way
education.
to determine a risk.
Yeah, so we're trying to replace, because that's what I said at the beginning. Insurers are looking at in which group of the society the riskier behaviors are, instead of identifying what is risky and who is risky. So you're like solidaire, you're like like people, like if we take like gender in kilometers, so what the result, like what we obtain like result, and what the other research obtain like result is that if men are more or usually riskier than women in the tarification when we don't use the exact kilometers, is that it is because like men under-evaluate their annual kilometers, and then women the other way around. Men underestimate what they are usually drive, and women overestimate what they drive. So
Roxanne, I'm gonna have to stop here. But thank you very much again, Roxanne. The next speaker, Marlon Moresco.
That's it. Okay, there you go.
Hello, everyone. Nice to be here. I will show the work that I did as a postdoc here in Concordia with Melina and Silvana Pesenti. We studied how uncertainty propagates in a dynamic risk measure, right? So, for starts, this is a work on risk measures. We see risk measures as an axiomatic view, right? And for us, risk measures is a map that takes a risk or a loss and gives us a number. In most cases, its input is a distribution. You put a distribution in a function, and then you get better how much the distribution, how risky is the distribution. You get how much capital requirement you need, and you get how risky it is. So that is what we are studying here. However, we have some uncertainty in this process. Kind of different than the uncertainty that was present in the other talks. This uncertainty is in a more like a Knightian sense, right? It's not a point for you that you are uncertain about the point forecast. You are more uncertain about if you got the right distribution, if you look at the right probability model, if you have the base probability model. Our approach even allows to have uncertainty if in the utility function on the risk measure itself. You may be using the wrong risk measure. So this is not new. There are a lot of research that does that in very different ways. What we do is propose a unifying approach. We propose an approach that can encompass all the other propositions of uncertainty that are in the literature, right? So what we get is a robust risk measure. This work is most concerned about the axioms and properties of this robust risk measure, right? If you have a risk measure, if it satisfies some properties, it will be a coherent risk measure, for example. And we want to be sure that it doesn't matter how, or depending on how, even if you take an uncertainty into account, you will still have a coherent risk measure that is robust for that kind of uncertainty that you took in account. So for generality, maybe, we work on a space of discrete and bounded process. So we look at the process of losses that occur in a finite time, discrete and finite time. So as we are working on a discrete stochastic process, we need to use dynamic risk measures, right? And our uncertainty will be measured by a set function, right? And u, set function u will take a random variable and gives a set of a set of random variables that may be the right choice. If maybe you are measuring the risk of x, but what you really need to measure is the risk of x prime. The distribution of x is normal, but your real data came from some other distribution. So this uncertainty set would contain all possible candidates for this true distribution that you are looking for. Right. We are looking for a stochastic process. So the uncertainty, we call that uncertainty set, and it takes a process, right, and gives back a set of random variables. When you look at the whole collection of the uncertainty sets, each time we have a new uncertainty set. So when you look at the whole collection, it's a dynamic uncertainty set. That's just to keep consistency with the literature of dynamic risk measures. Right. So a simple example to make it very clear on everyone's mind. If you have a random variable x, the simplest uncertainty set around it is just a ball, a closed ball around x. The norm can be however norm you want. And you take every other random variable that is close to x in some sense. In this example, we say that it's closed if it's norm closed. But you can take that norm to be any norm or semi-norm or some distance function. Can be the Wasserstein distance or Kayal divergence or whatever. You can go crazy with that. Whatever suits your needs, you can choose that. And most literature have the Wasserstein or Kayal divergence there. And they do research on how to compute that and bounds for this kind of a thing, and our approach allows us to see everything in the same framework. I like to highlight the epsilon, that's the size of the ball. In most of the literature, this epsilon is fixed, but we allow it to change. An example of epsilon that changes is setting it to be epsilon times the variance of the random variable. So as you get closer to a constant, you are more certain of your distribution, and then your uncertainty set kinds of shrinks. But again, most cases use it constant, but we allow it to change. So our question is, what kind of properties those uncertainty sets that set functions should respect? What properties make sense, right? The first one is proper. What we call a proper uncertainty set is an uncertainty set that's non-empty and bounded. Because, well, if it's either empty or non-bounded, then it's kind of too big or too small. It doesn't really make sense to use. So we always ask for the uncertainty set to be proper. The second property should be normalization. Normalization is a property that you can argue for and against, right? You can argue that, well, if you have nothing, you have no uncertainty there. You have nothing, so what are you uncertain about? So the uncertainty set of 0 should be 0. There's no question there. But if you think of a hedged position, it has cash flows or flow of losses equals 0, but there still may be some uncertainty there, right? So it would not be normalized. If you think about this example, if epsilon is constant, then this is not normalized. So most literature of dynamic risk measures, they assume normalization, but we will not. So we do some changes on what's more traditional in that literature to allow for a non-normalized uncertainty set, because it may be what really represents the problem that you may want to tackle. So another property that's quite central is order preservation. What means order preservation is that if you have two ordered losses, then the uncertainty set will be in some way also ordered. By that I mean y is a loss that's greater than x. Then once you draw the uncertainty set around y and x, you take any other loss inside the uncertainty set of x, you can find another loss in the uncertainty set of y that is still greater than x prime. You can find an y prime that's greater than x prime for any x prime inside x. So the uncertainty set kind of preserves the order of the random variables that's looking into. This is important because in principle, the uncertainty sets can be very different for two different random variables. They doesn't necessarily need to follow the same rules for two different random variables, right? Even if you take two random variables with the same distribution, they may generate different uncertainty sets because you may have more data in one than the other. So you may want to have an XY with the same, and you estimate the same distribution on them, but you have more data in one than the other, so the uncertainty around one is maybe greater than the other. That's why we allow, that's not about order preservation, it's about epsilon. That's why we allow epsilon to change with x. Then the other property is translation invariance. Translation invariance tells us that if you have some measurable random variable, you can think of this as a constant, right? Because it's a measurable random variable, so it behaves like a constant. So if you have a constant added to your handle process, you can take this constant out. So it will shift the uncertainty set in the direction of the constant, as it may be expected. May not, but it's very reasonable. So if you have those four properties, normalization, order preservation, and translation invariance, your collection of uncertainty sets will look like this, kind of. Because if you have translation invariance and normalization, the set of constants will be a singletons. All the uncertainty sets of a constant will be a singleton. And as order preservation implies that there is some kind of order between uncertainty sets, the uncertainty sets will be kind of shrinking as they get close to a constant, right? That's kind of behavior that happens when we have those properties. We are studying dynamic uncertainty sets, so we look in a time frame. But if you want to look in the one per period, you can use a static uncertainty set, and pretty much all of our paper also works very well within a static framework. And to tackle that, we introduced the property of a static uncertainty set. That's just, it does not depend on the future, it depends on the random variable at time t. Right? We also have positive homogeneity. That means that when you scale, lambda is a measurable random variable. We can see it as a constant, the same way as in translation invariance, right? When you scale up a process, the uncertainty set will also be scaled up in by the same number. We modified a bit of what may be used to positive homogeneity, because we want to account for non-normalization. In most cases, for risk measures and for us, in positive homogeneity implies normalization. And we want to have positive homogeneity, but we do not want to necessarily have normalization. So we add this term. That's whenever lambda is 0, we add the uncertainty set of 0. If the uncertainty set is normalized, then this guy just disappears, right? But if it's not, it keeps everything consistent. And then slightly generalization of positive homogeneity is star-shapedness. This is a pretty new property in risk measures. There are a lot of people studying that in this year and last year. It means that the uncertainty set increases faster than the size, the position. If you increase the position, if you increase the position by 2, the uncertainty set will enlarge by a factor of more than 2, right? Or as written, if you shrink the position by a factor of between 0 and 1, so you're shrinking the position, the uncertainty around that position will be shrinked by less than what was shrinked before. Right? We still do the same factor to account for normalization, right? For non-normalization. In the paper, we also have a few more properties, like we approach convexity and subjectivity and locality, but I will not go into those because they are more technical maybe. But for each of those properties in the uncertainty set, we have an equivalent property in a risk measure, right? Star-shapedness, we have a property of star-shaped risk measure, positive homogeneity risk measure. We can define a static risk measure, a translation invariance. and proper, and for all those 7 properties, there is an equivalent property in risk measures. And what we do in this paper, pretty much one of our main results, is show that each of those properties in the risk will be linked to the property of the uncertainty set. They will be a link. I will show the link soon after, but there will be a link. So going back to the example that I showed before, if you have the same example with a same norm, that same norm will be proper, normalized, or preserving, translation variance, and static, positive, homogeneous, all those stuff. If it satisfies some right condition on epsilon, right? It will always be proper. It will be normalized if and only if the function that we had inside there is a norm, not a semi-norm, needs to be a norm. And if we set this to epsilon of 0 to be 0, right? We can do that. It's just not what people do when they use this in the literature, but it's possible. It is order preserving under some condition on epsilon again, translation invariant, static, and all those things. If instead of using a norm, you use the Wasserstein distance, you also satisfy pretty much the same properties. You also need some requirements on epsilon, right? And if you use a Kyle divergence, then you satisfy all properties pretty much automatically. You don't need much conditions on epsilon. It's because Kyle divergence goes to infinity if you don't have the same support of 2 distributions. This pretty much gives everything away. You can define the search set not just as balls, you can define it as many other things. One of those things is you can change the base probability measure of the space. And you have X and you have a Q set of probability measures. And you look at this at X under each probability measure on the set Q. And then this uncertainty set is again a set of random variables that are based on different probability measures that don't even need to be absolutely continuous to P. It makes sense to be, but doesn't need to. And this set also satisfies pretty much everything that we want. So it's well behaved. Okay, now we propose the uncertainty sets. We have some definitions and properties of what is a good uncertainty set. This camera, no, that camera. What is a good uncertainty set? So now we want to propose a risk measure that is robust to the kind of thing that you define your uncertainty set. You can define your uncertainty set to protect yourself to different kinds of uncertainties. And then you want how to make your risk measure to be robust to that uncertainty. Well, the most direct way is just take a supremum. You have a conditional risk measure ρ, a one-step risk measure. You can choose wherever you want for here. It should be, I wrote coherent, but it needs to be just normalized, monotone and translation invariant. You probably choose something like expected value, expected shortfall, or whatever fits. We show in the paper that doesn't matter which you choose, you can always have a representation with the expected value and a kind of different uncertainty set. So you can, a risk measure is a kind of way to measure uncertainty in not Knightian uncertainty, but it's a kind of way to measure uncertainty. You can always transfer what the risk measure is measuring to the uncertainty set, but you cannot do the opposite. You cannot transfer the uncertainty of the uncertainty set to the risk measure. It's not possible for all cases. So a robust risk measure is the supremum over all risks inside the uncertainty set. This is what we propose. And most part of the paper is showing that for each property each axiom that the uncertainty set satisfies, the robust risk measure also satisfies. So if the uncertainty set is in a way coherent, is translation invariance, positive homogeneous, convex, order preserving, then R will be a coherent risk measure, dynamic risk measure, right? So the main contribution is showing what's sufficient conditions on the uncertainty set so that we have a well-behaved, robust risk measures. So we have kind of a problem. By now we have defined what are sufficient conditions on the uncertainty set, but we don't have the necessary conditions. That's because two risk measures, take an uncertainty set that's translation invariance, for example. You can always find another uncertainty set that's not translation invariance and gives rise to the same robust risk measure. So the uncertainty risk measure is in a way not unique. You can always, that same thing that I said about translation invariance also happens for positive homogeneity, for monotonicity, for order preservation, all those kinds of things. You can always find another uncertainty set with the same robust risk measure that does not satisfy that nice property. So one may argue that those properties that we introduced before are too strong, right? Because, well, we can get the same result without them, so the property must be too strong. So how can we guarantee that it's not too strong what we're asking? We want to get if and only if kinds of statements. We want to have to say that the uncertainty set is translation invariance if and only if the robust risk measure is translation invariance. In this way, we guarantee that what we say that of translation invariance for uncertainty set is not just enough, it's not too much, right? So to do that, we introduce a kind of unique uncertainty set. So we call that consolidated uncertainty set. So for you take an uncertainty set, you get a robust risk measure. Now you look at all uncertainty sets that have the same robust risk measure, and you simply take the union. So you take the union of all uncertainty sets with whose robust risk measure coincide. And that guy is the consolidated uncertainty set. It has a few more tractable forms, right? It's equal to the set of all positions, all losses, such as the risk measured by the risk measure that you use is smaller than the robust risk measure. It's also the same as the acceptance set of the underlying risk measure plus your robust risk measure. So it's much more easier to track in those two forms than in this guy here. But this gives us a kind of a unique uncertainty set that is associated with each robust risk measure. So that's very useful. And from this, we get those if and only if statements for all properties that we talked before. So again, I talked about what I talked about just now could be very well done in a static time. We also work on but we do our work on a dynamic framework. So we care a lot of time consistency. We care a lot of how our risk measurement procedure, of our uncertainty measure procedure will happen through time, right? And the strong time consistency that appears in the literature is this kind of recursive form, right? You can always write the uncertainty set as some kind of sum in there. This is a recursive, it has a recursive nature, right? So as we are very worried about non-normalized uncertainty sets, we kind of fix this property, the strong time consistency, for non-normalized risk measures and uncertainty sets, and it takes this form. Weak time consistency is very similar to the ones before, right? But it has an inclusion process. It means when you look at the process at an earlier time, you kind of have less uncertainty because the time frame is shorter in a way. Order time consistency in many times is equivalent to strong time consistency. Means that if you have two processes that are exactly the same up to some point S, and from S onwards, one has more uncertainty than the other, then when you look at the uncertainty of the whole process, the one that had more at just S onwards will also have a greater overall uncertainty. Rejection time consistency means that if you have 0 inside of your uncertainty set, it will have in the future 0 is also contained in your uncertainty set today. And prudence means that the process is kind of contained in the uncertainty set. That's pretty much the spirit behind prudence. Again, for each of those properties, there is a counterpart in risk measures, right? Except for prudency, but there is a counterpart. And we show that each of those properties is an if and only if condition for the analogous property in the risk measure, the robust risk measure, right? So here we show, this is not necessarily new, but we do it in very detailed, which kind of time consistency imply in the other. So if you start with strong, you get automatically the non-normalized, and then if you have monotonist, you get other time consistency. Then with normalization, you get rejection time consistency, and you have a whole diagram here of implications on the notions of time consistency. Those implications are kind of well known in the literature, but not as specified. You normally start with an normalized monotone translation invariant risk measure, and then you have those equivalents. Here we have a bit more detail. And then I wouldn't say the main result, but a very interesting theorem in our paper is how you construct uncertainty set or a dynamic risk measure or dynamic uncertainty set from static uncertainty sets, right? Because in the literature, this kind of robustness is mostly concerned about static case. So there's few stuff on dynamic. And here we show how to take that, whatever you have in static and expand for a dynamic case. You do that recursiveness nature. You take an uncertainty set of the process, you take an static uncertainty set and define your dynamic uncertainty set as in a recursive way. You take the risk, you start measuring the robust risk measure at the end time, and then at the time before and time before to get the time t uncertainty set. Then again, we have that if the original static uncertainty set satisfies the right properties, then the dynamic uncertainty set will also satisfy those properties, and the robust risk measures will also satisfy those properties, and everyone will live happy after ever. And that's it. Thank you for your attention.
Is there, yeah, Sebastian, quick question.
Me again. In slide 10, if you can go back, I was just wondering, yeah, star shapedness versus positive homogeneity. Isn't positive homogeneity kind of a special case of star shapedness?
Yes, yes.
Okay.
Star shapedness is a kind of generalization of positive homogeneity.
Okay.
If I say it otherwise, it's because I missed my words.
Okay, yeah, I just stayed stuck on that. Thanks.
Yeah, no, yes.
Thank you very much, Marlon.
Thank you.
We'll have our last speaker, Rishikev Yadav.
Okay, good afternoon, everyone. And my name is Rishikesh, and I'm a postdoc at HEC Montreal. I'm currently working with Aurélie Lobe from HEC Montreal, Alexandra Smith from McGill University, and Pratibha Jagannathan from McMaster University. And before I start, I would like to thank Chris and Melina and others for organizing this wonderful session. This is really nice. So today I will be presenting my current ongoing project, modeling of sparse conditional spatial extreme processes subject to left censoring. And this is a joint work with Leo Belgile. He's a assistant professor at Department of Decision Science, HEC Montreal, and Nicholas Beck from Jelus Analytics. So my our main motivation is behind 2021 British Columbian floods, where essentially 24 British Columbian communities received more than 100 millimeters of rain in just a span of only 3 days. And in particular, for the town of Hope, during these 3 days of periods, an estimated 250 millimeter of precipitation. That's a huge amount of rain for a very short interval of time. And this is one picture essentially taken on November 23, 2021, where you can imagine the severity of the event. So we extracted the gridded British Columbian precipitation data from the PCIC repository for the time period 1950 to 2010. And this is essentially, we found it as reanalysis data. And it was essentially very fine graded because somehow it was like downgraded. The climate outputs, and in particular here for this analysis, we randomly selected 200 spatial location over some part of British Columbia, especially the region where our particular interest is. So in the left plot, we have average precipitation in millimeter taken over the whole time period 1950 to 2010, and we can see very familiar, I would say, patterns, spatial patterns. Especially, you can also see the effect of Cascade Mountains, and then also the effect of coastal areas. And in the right side, we plot the conditional average given large rainfall near Abbotsford. That's Abbotsford is the region where essentially I showed the picture earlier where the floods occur. So conditional on that we have a flood or we have a large rainfall near Abbotsford. The plot is a bit, you could say, just a bit different than the overall average rainfall. So here, as it is very general truth with the rainfall data is that as the intensity of the rainfall increases, these events gets more localized. And we also know that there is zero inflated data. Either we have no rain or there will be a positive rainfall amounts. So here our goal is to construct a stochastic generator and create a catalog of daily cumulative rainfall fields given exceedances at one particular site. So for this exceedance, the conditioning site we choose is the site that is very close to the Abbotsford region. And here both marginal and spatio-temporal dependence are of interest. In particular, extremal spatial dependence. We are mostly interested on the extremes of extremal dependence of the event, given that we observed high rainfall at one particular station. So conditional spatial extreme value model is one sort of models that model spatial dependencies conditional on one particular site. So consider a stationary random field Xs, and it has transformed to have a standard exponential tail. And then we model the spatial dependence in this process, given that the conditioning site exceed a large threshold value U. And we suppose that there exists a scaling function A and B such that conditional on exceedance, the scale process converges weakly to a non-degenerate spatial process. For example, we say it's a residual process, and it satisfies that at the conditioning site, this process is equal to zero almost surely. And the conditional excesses at conditioning site also converges to extreme exponential distribution with rate 1, and it's also independent of the residual process. So we can use these theoretical results in applications to write as a location scale family of models where the normalizing function A and B, A can be treated as a location function and B can be treated as a scale function, and Z is a residual term. For example, we may assume as a Gaussian distribution for here. And this essentially the normalizing function A and B measure the spatial dependencies, and it also captures the strength of spatial dependencies. And this one of the paper that lists the conditions that's in function A and B that guaranteed valid limiting models. And in particular, we can take the function A of this form, where rho has to be a kernel that decreases monotonically as we go far away from the conditioning site. For example, we can take it as exponential correlation function with range parameters kappa A to be estimated from the data. And in particular, due to the topography of the British Columbia, because of the Cascade Mountains and the other things, we expect that there will be very different dependence in different directions. For example, we expect that there will be a similar types of rain along the Cascade Mountain from north to south, I would say, and then we will have a very strong spatial dependence on that direction than the west to east. And similar things will happen when you move to the more coastal areas. So we capture this by incorporating in so-called geometric anisotropy in spatial statistics, and this is and the two of the parameters for example, anisotropy radius r and angles alpha should be estimated from the data, and for the scaling function b, we assume two different models, M2 and M3. That's what listed in the Wordsworth and Thorne. and some parameters to be estimated from the data. So there have been several literature and several work have been done on using these COSPEX models and using it and applying it to different sort of data sets. But the main challenging part with this COSPEX modeling is the inference often. Because the modeling of COSPEX, inference of the COSPEX requires that the marginal distribution have to have a unit Laplace scale tails. So it's hard to combine the margins and dependence together. So often people opt with the two-stage estimation techniques. In the first stage, what they do is they estimate the marginal distribution either parametrically or non-parametrically or semi-parametrically, mostly site-wise. And then they use some sort of probability integral transforms to transform the data to standard Laplace scale. And then they use COSPEX models to do the spatial dependence. So, and mostly frequencies approach have been applied, except for the two of the cases who uses INLA, integrated nested Laplace approximation. This is another way of doing deterministics approximate Bayesian inference. But it still lacks novel application in high dimension. And another thing with the extreme value theory is that often we care the good modelings in the tail of the distribution. So what we want is we don't want to corrupt our models, or we bias our models with the data that are not essentially required. For example, if our goal is to model the upper endpoint of the distribution, for example, the right tail of the distribution, so we want to censor the observation that are low. And often in extreme value theory, the classical extreme value theory, the models are built in such a way that when we apply the left censoring, the likelihood involves a high dimensional Gaussian integral. So that's essentially restrict the application of this COSPEX model, or in particular, most of the extreme value models to fit in high spatial dimension. And that's also true with the COSPEX models too. So, and censoring is only considered by one of the papers here, Richards and others, and they use composite likelihood, which is essentially an approximation of the full likelihood. So they use this composite likelihood techniques to do the COSPEX, and while doing the censorings. When I say censorings, they are censoring the non-extreme observation or the lower observations to remove the bias while estimating the right tail distribution of the data. So the objective and contribution of this paper is mainly involves in two contributions. The first contribution is that we essentially enrich the COSPEX models by establishing a computationally feasible way for handling large scale inference in the presence of censoring, but still using the two-stage estimation framework, but use the full likelihood inference and the data augmentation techniques that I will explain just in after a few slides. And the second contribution is simultaneously estimating the marginal parameters and dependency structure, because essentially so far the work have been done only modeling for margin first and the dependence structure separately. So our goal is to in fact do both together, because we know that there is plenty of uncertainty in the margins. And another motivation of doing or modeling simultaneously marginal parameters and dependent structure is that there was some sort of mismatch in the Laplace marginal distributions and the actual marginal distribution we get from the model. So this was a sort of a mismatch when we do the two-step approach. So in this presentation, for time's sake, I mostly cover the details of C1. And if you have a questions, I will I will be happy to talk about for C2 as well. So first I will talk about the marginal modelings. So essentially what we do in these papers, we estimate the marginal distribution site-wise using a mixture of 3 distributions. So for example, we have a rain and non-rain. So for that part, we do logistic distributions, logistic distribution, and for the positive precipitation and that is below than some high threshold U, we use empirical distribution, and the positive precipitation that are very extreme or higher than the given threshold U, we use a generalized Pareto distribution. That's one of the extreme value distribution commonly used in the extreme value theory literature. And in order to estimate the threshold U for the generalized Pareto distribution, we use a thin plate spline models with the covariates given by the latitude and longitude. And once we finish the marginal modeling, we transform the data to a standard Laplace margins using probability integral transforms, and hence we can move ahead with the cost-specs model. So we here consider the modified conditional process, which is essentially just taking the same location mixture model from earlier and then adding the IID term epsilon of S. This is considered to be a nugget effect in spatial statistics literature, and we assume that it's IID Gaussian distribution with variance tau square. So what is the advantage of this is that now we can, now our data is conditionally independent given this residual vector Z. And now this, now the joint distribution, I would say, will be product of univariate Gaussian CDF and Gaussian densities, where QJ is basically high threshold, censoring threshold. So if the observations are below some threshold, we have a Gaussian CDF, and if it's greater than QJ, we have a Gaussian PDF. So essentially, the earlier what we have is like if we have D sites and we censored, for example, at for example, half of the sites, then our integral was phi d over 2, something like that. So that was really difficult to handle. But with this data accumulation techniques, you come up with a likelihood that are much simpler, and it's essentially just product of univariate densities and univariate CDF that are easy to calculate. But now this is not as easy as we think, because this involves the imputation of residuals vector Z. And essentially, if we have a D sites over the spatial region, then it requires order D to the power 3 flops for each time replication, which makes these things still unscalable. If we have a higher dimension, then this really gets make every modeling a bit slow. So what we propose is fusing, approximating this residual process Z using a basis approximation based on the stochastic partial differential equation approach. So what essentially it does, it creates, so what we do is like we have a spatial domain, and then we put some spatial knots or it's called mesh knots around the study region. And the good thing is that this essentially this knots or this mesh knots doesn't have to be as order of the data. So for example, if you have thousands of locations, you can just put maybe 100 or like 1,000 or like 500 of mesh nodes around the study regions, and this W is essentially of that dimension. So that depends essentially on the mesh. And another good thing is that this W has a Gaussian distribution, and the covariance matrix involved in this Gaussian distributions is essentially inverse of the sparse precision matrices. So the computations is really simplified because of this precision matrices. First thing is that this Q is a sparse precision matrices. So calculating the Gaussian likelihood is super easy and super fast. And another thing is that this the dimension of this matrix Q doesn't depend how many spatial locations you consider, but depends on the how many mesh locations you choose over the study regions. And here the project A0 is a projector matrix that basically project the mesh node locations to the spatial location or observed locations that we have in our study region. And here epsilon z, we choose it to be again nugget terms with one of the parameters or variance parameters to be estimated. This is simply added to benefit two things. First thing is that it's solve the computational problems in the Bayesian inference that I will talk just now, and it's also captures any unstructured errors that are present in the at the latent level. So this is the hierarchical formulation of the model. So this is the hierarchical formulation of the model. So we can capture the pieces of the information so far I presented, and then we can put them in a Bayesian hierarchical formulation. So what we have is like at the data level. So we have this is just the univariate density, as we say. And what we have here, that's the residual terms conditional on this basis weight. That's what we say. This and these parameters, it's again a d-dimensional Gaussian distribution, and this basis weight is basically a k-dimensional multivariate Gaussian distribution. So where k is the number of mesh node location, here k is much less than the d, depending, and it approximates the true process pretty well. And this theta is basically the hyperparameters of the model. So what we do is like we utilize this hierarchical formulation of the models and propose a Markov chain Monte Carlo method to draw posterior sample from the models. And due to the structure of the models, we have gives updates for the weights W, because we get the full conditional distribution for the W. We have a Gaussian case, so conjugacy helps here. And then for the parameters Z, residuals parameters Z, we didn't have a closed form expressions because we have due to the censoring terms here. So, but the good thing is that because we have independence and independence both here, so we can update this high dimensional Z parameters in parallel using Metropolis Hastings algorithms. And for other hyperparameters, model hyperparameters, we just use a standard normal walk random Metropolis Hastings algorithm. So we do some simulation study to check that everything is aligned and working fine. So what we do is that we fix the hyperparameters values from the models to some reasonable values, and then we use the hierarchy of the models to simulate from the model. So this is the true values of the models are set to be some reasonable values, and we simulate the spatial site in a uniform grid. It's not grid, it's like randomly into 0 to 10 square. And this is the posterior mean, and then the bias, and then the standard errors. And this is total effective sample size. This is just asset that the Markov chain samplers are doing well. And we can see that the bias in the parameter estimates are pretty low. I mean, it's not huge, and especially the 95% credit intervals covers these estimated parameters values and the true values, and the total effective sample size are reasonably well as well. With this, we move to the data application part. So as I talked earlier, so we do the two-stage approach, but now with the censoring. So for the marginal models, I did the same. I just fit the mixture of 3 distributions, and then here I randomly select 6 particular stations from the study regions, and then I plot a quantile plot, and we can see that the marginal fits looks quite okay. So with this, we can use the probability integral transforms to convert these marginal distributions to have a unit Laplace scale. So with that, we did the dependence modeling. So what we observed from, what we get from the models, this is the interpretation of the parameters estimated from the model. So essentially what we get is that the normalizing functions, hyperparameters in the normalizing functions are appear to be the same. So what it means essentially is that indeed we have a short-term dependence in the data. That was quite expected because that's happened with the precipitation data. That's when we go to the extreme, especially the events gets more localized as the intensity increases. And then we have a moderate spatial dependence at the data levels. And the two estimated nugget parameters are estimated to be very close to 0. That suggests that the most of the uncertainty in the models are captured by the fully structured component, and the independent component contribute very less. And the anisotropy parameters, estimation of anisotropy parameters suggests that there was a moderate anisotropy. And in fact, the anisotropy angle, this angle suggests that there was along the Cascade Mountains regions, we see a stronger spatial dependence. So with that, I will summarize my works. So what we do is like we use a sparse residual process with data augmentation to effectively deal with left censoring. And we propose an efficient full likelihood based inference based on Markov chain Monte Carlo samplings. And we also propose an unified framework for modeling jointly the marginal and spatial dependencies. So some of the works are still in progress. So for example, one of the difficulty, or one of the I would say that lacking thing in the data we saw is that because we found it's reanalysis data. So it was downscaled data. So, and it's downscaled in such a way that it's over smooth the data. So when you over smooth the data, is somehow you kill the, the local, how to say, the local extreme. So that's what, so for now we have now the observed data. So that's station-based data. So our goal is to compare and see actually if we get a similar or completely different behaviors when we use observed data instead of reanalysis data. And another work in progress was making this joint estimation framework that was mentioned, contribution C2, to make it fast, because for now we were some sort of using copula to combine the marginal and the dependence together, and this involves non-closed form density that's essentially involves the integral. So if we had, like, for example, d site and t time replicates, in total we had the d times t integrals at every MCMC iteration to be considered, and we were doing some sort of some Monte Carlo approximations to approximate the density, but that makes MCMC algorithms really slow, even if we have a moderate spatial dependence. But what we managed to find is like doing it by the deep learning based approach. So essentially what we are currently doing is like we are doing it in an amortized function. So what our goal is to estimate the density, conditional density. So what we do is like we train it at once. So given the geographical region or given the area of interest, we train it for like very long time for very fine parameters, values, and the spatial locations. And then we can, in our MCMC algorithms, we just predict at the location. So this works pretty fast. So this is still, we are kind of working on it. So with that, I will thank you everyone for still being here.
Thank you very much. Are there any questions?
In your matrix, covariance matrix Q, you were showing, I think, around slide 12, there's that row. Am I right in thinking that row is that correlation between your different sides that is measured by your kernel?
Yes, it's a sort of correlation, yes.
Okay. And that kernel, I'm still having problem when people make spatial model with that kernel, because that kernel is really important to model the spatial dependency.
Right.
And it's great you can consider anisotropy by orienting your kernel.
Right.
But what about discontinuity? You're in a mountainous region. If you're on one side of the range versus the other side, the correlation is based on distance, whereas it can be completely decoupled. Whereas any kernel approach you're going to use won't be able to account for these kinds of things. And I feel that this has to have like tremendous impact on the results.
Right.
Any way to get away from this kernel?
Right. Actually, there are some kernels like that. So one thing I mentioned is the geometric anisotropy. So that's true. It's isotropy. You cannot expect it like isotropy, because isotropy requires you to be everywhere the dependency. I mean, like if you pick here, everywhere the dependency is same. But you are right but the way you could do it like anisotropy is one way to do it. And there are ways like, for example, non-stationary version of this Q matrix. So for example, here row is fixed now here, but instead you can take row to be varying over site. So every spatial location, this row is different. So you can use this information. So there are ways. I mean, in fact, this matrix is taken from the INLA basically. So they have done some work related to this. I think that could really work like with these situations. Yeah.
Thank you. Can I go for a
will
tiny question?
Yeah.
So you mentioned in your conclusion that you were observing some kind of over smooth result.
Yes.
Could it be because the reality is a kind of superposition of different scale, in a sense where you can have a macro system of rain coming in, and within that macro system, there's some local pockets. So there's spatial dependency within the spatial dependency.
Right.
Whereas if you just have one stochastic spatial process to model everything, it's going to be over smooth because it's going to be the average of the local and the global processes.
Exactly, that's true.
Could it be something?
I agree with you is essentially, but over smoothing, I feel like here we had this different things. I mean, like here, because I think that, the originally the data were like from a climate data, and they downscale it. So that the way they downscale it, for example, they just interpolate the data. And when they are doing the interpolations, they are using, I mean, if you do some sort of like proper statistical model, probably you will not get like very smooth. But if you get some types of spline or just doing something like that, would be very smooth version. So I feel like in this data, we have something like that actually in the reanalysis data. But in general, that's true. I mean, like, this will always be on debate, like using a global model or like a regional models, or like one single models for the whole regions is never going to be enough. That's true.
Super, thank you.
Yeah.
Any other questions? Maybe it's related to C2, so you didn't talk about it that much, but did you consider at some point when you talked about using copulas for every to join the distribution of every site, did you consider maybe doing clusters of copulas, which could help having a less heavy model if you would join all sites?
Actually, we haven't thought about that. So you mean the cluster?
When you have each station, and then you said maybe using copulas.
Yes.
So if you would do some clustering of your sites, which could reduce the size.
Okay, I see.
Of the joint model.
That could be one way. Yes, that could be. But our main issue arises from like at this level essentially, because of this essentially. These terms essentially. So this doesn't have the closed form expression actually, fj of inverse and these things. So this is all univariate problem, is still univariate. Everything is univariate because of the data augmentation.
Yeah.
But the main issue we were feeling like is doesn't have a closed form expression, and this j is equal to 1 to d. So we have a d site, and if we have a temporal replicates, we have a t time points, and that's make it to the n d times t. So d times t. I mean, at every MCMC iterations you can imagine. So that was really slow, but yeah, you are right. We could thought of in some sort of clustering way, so we could probably reduce some of the calculations. I mean, but that will lead another question, like how we choose the clusters, and then yeah. So, but
yeah, there are some algorithms.
Yeah,
but
right. Yeah, that's a good point. Anyway, thank you.
Thank you very much. Are there other questions? If not, thank you again. And we do have a reception, so if you want to take the elevators and reconvene on the 9th floor. And other than that, thank you very much, everyone. Thank you all, those of you who presented, and maybe see you upstairs.
Thank you, everyone who joined us online and in person. We're about to close up the Zoom for the day. Thanks again. Have a good afternoon.